Alright, hell yeah. So we have 3 hours, 1 problem. But I'm going to give you a 5-minute solution, so that's pretty sweet. This is a very challenging, or red-starred problem. And we have a soccer person kicking a soccer ball from the top of a rock. This is a half of a dome. It's a hemisphere, it's a hemisphere. Sweet. And we want to know what the initial velocity has to be so the soccer ball doesn't bounce down the dome. Okay, hell yes. So, and then once we find that initial velocity, we need to find the distance from this point that the soccer ball hits. And hell yeah, let's do it. Cool. So the 5-minute solution is that here's the equation of a circle. And so if we throw in a value of x, we're going to be at a height of r. And as we travel an x distance this way, we're going to map out that circle. So that's what we're going to see from the side view. Here's the kinematic equations in, you know what I mean? And I already did the integration. So in the x direction, we don't have any change in velocity. And so our position is just that velocity times time. Our position in the y is constantly changing. The soccer ball is falling to the earth. It's getting faster and faster in the negative direction. It's going to start at an initial height of r, and this is the equation for that. Now, what we want though is a y equals x equation for the soccer ball. So in kinematics, those two equations are a function of time. They're not going to show you how the soccer ball is visually seen from a side view. So these problems are pretty sweet because we have to link these two equations together, knowing that at any time, if the time value here is 1, the time value here is going to be 1, and those x, y coordinates are going to be the coordinates in the x and y direction that you see the soccer ball. So those are similar. So I'm going to solve this for t, and then we shove it into here. So this becomes x squared divided by v squared, and then we have the rest. So now we have two equations, y is equal to x, y is equal to x. This is the equation of the dome. So if on a graph, we're going to do that, and then the other one is the graph of the parabola. We're still not done though, because this is still a function of the velocity. What we want to make sure is this parabola never touches the dome. It's going to be touching right at the top where the soccer ball touches the dome. But when we kick it, the soccer ball never touches the dome again. All right, so how do we solve this? And this took me, well, I did a lot of explaining, and so enjoy the video if you want to watch the whole thing. But at the end, I got stumped. I had no clue what to do. And so this was my solution. It's probably not the most glamorous, but it is a unique solution because it allows you to look at the equations and be like, how would you solve it? Because what you'll see in the 3-hour video is we just kind of throw numbers at this and we get the answer pretty fast. But then when we actually have to use the math to solve for this value in a technical way, I don't know, I just wasn't able to do it. And so what we do is we're going to say that these two equations we're going to equal them together. But what I want, and more appropriately, I always want this one to be smaller. So this is the y value for the hemisphere, for the rock. And then this is going to be the y value for the soccer ball going through the air. This should always be bigger. Because if it is smaller, then we know the soccer ball hit the sphere. That's why this is smaller. Now, how do we analyze these? What I did is I just squared this side and squared this side. But now, like, how are you going to be thinking about that, and why would you be thinking about that? And I was trying to think of different ways, like, could I take derivatives? Does it matter with the slope? And I just couldn't figure it out because even though the soccer ball could miss up here, it could come back and hit. And then so honestly, this solution is only useful for like, hey, the first little bit. But I don't know, maybe it is a technical solution. You be the judge. So what I did is I squared both sides, and still this side has to be smaller. So we just get rid of the square root here. Now to square this side, I'm going to have this whole thing squared. So we got positive 25, x to the fourth, and v to the fourth. And then I'm going to square this, r squared, and then I'm going to have that middle term. It's going to be this times 2. So that's where I get the negative 10r, x squared divided by v, I squared. Now, if x is really small, like, you know what I mean, the position of x is just really close to where the person kicks it, then x to the fourth, a small number to the fourth, is ridiculously small. So I'm just going to cancel that out. And then what we have on both sides is we have an r squared on both sides. And then so the only term that drives is this negative x squared and this negative x squared. It just has this out in front. So I notice this has a 1 out in front, and this has a 10r vi squared. So this has to always be bigger. So, and I should have, this should be equal to or greater than. So we do a greater than sign, greater than sign, greater than sign, and booyah. And cool, now we just bring the v squared upstairs and then square root the other side. Now this vi has to be, and I probably switched it around. The second I take, I have no idea what's going on. But yeah, let's think about this. This has to always be bigger than 1. Is that even going to work? My mind is fried. But anyway, let's just say they're equal, and we'll figure that out up here. So, let's get rid of the great. I can't stand greater than, less than signs. But here is where it will touch. This is the velocity max. And now we're going to take the square root 10r. And if we plug it into here, and this velocity has to be bigger than, it has to be bigger than, because if this is bigger than square root 10r, let's take a look at this, because it's because of this negative sign. I probably shouldn't have got rid of the negative sign. If I didn't get rid of the negative sign, I think I'm good with this thing going on. No, sorry. My brain is fried. But anyway, so if we increase the velocity, we'd probably go up here and look at it. But if we, but from here we can probably do it. Chill it out. If this is our velocity, square root 10r squared, so this is going to be a 10r downstairs divided by a 10r, and then we have a negative, and this is negative 1. This negative 1 is equal to negative 1. If I increase this bottom, that means that this gets smaller, and then I'm going to have a negative. If this was both negative, so this is going to be like a negative 0.5. So is negative 0.5 bigger than negative 1? Yes. Yeah, negative signs are my nemesis. But there you go. So hell yeah. So this velocity has to be this or greater. And that's going to be our answer there. All right, so now what they wanted to know was, knowing that we have initial velocity, when's it going to hit the x? And we come back to our kinematic equations. We have to use both of them. One is saying that this is the equation of this isn't what we see. This is just y as a function of time. And so y is going to have a datum at 0. This is r in the y direction. When y is 0, I'm going to find a time value using that kinematic equation. That's why kinematic equations aren't what you see. It's just at that time it's going to be at this location. And if you have two of them, this is just for the y direction and this is just for the x direction. It's because these are vector quantities, and we can separate them into the two, 90-degree oriented directions. So when y is 0, get the r to the other side, is going to be a negative r, get rid of the negative signs, divide by 5, square root, and we have the square root of r divided by 5. And now this is the time that it would hit the ground, and now I'm going to throw it into the x equation, the kinematic equation. X is a function of time. And this one makes sense. If I kick this soccer ball, there's no air resistance, we're going to say, nothing impeding it, no force on this mass, and so it's just going to travel at the same speed, even though it's falling in the other vector direction. So we talked about that. These vectors do not inhibit each other, and so the time that it hits is going to be the time that it's still in the air in this direction, and that time times that velocity. So we have the velocity times time, and we just found the velocity, square root 10r, and then we have a lot of square roots. We can just square root the entire thing, and we're going to have an r squared. 10 divided by 5 is 2. That's what we have here. And then r squared is just r. So hell yeah. So we have the square root of 2r. Now this isn't x, my apologies, because this is the distance from the center. You know what I mean? Our datum, I put my datum right here. So that value of x is for here. This value of x, I'm going to call it just x star, is going to be the value of x that we solve for minus r. So hell yeah. And that's it. And it's just fascinating. And it's good for me to do these fast solutions. So x star for the problem is just r minus square root 2r, which is just r 1 minus the square root of 2. And I don't know, you know what I mean? I don't think it's the techiest solution, but this one's not in the back of the book. The answer isn't even. And you know what I mean? I ain't buying Chegg. So I don't mind if I'm wrong, because someone can point that out or point me in the right direction to get a more technical answer. But hell yeah. So now sit back, relax, and watch the 3 hours of, it's pretty good time. Pretty good time. And so this is what we do. This is, you know what I mean? Without further ado, you're going to be looking at this for 3 hours. So this was the problem. And hell yeah. All right, hell yeah. So a viewer wanted me to do a projectile problem. So I pulled up the physics engineering textbook that's used in most colleges. Now this is the author of Sarah Jewett. You can find this online for free. I just have the PDF. You got to be careful that you're not just going to get spammed with viruses, but this pulls up pretty easily. Hell yeah. So what we're going to do is just kind of go to the table of contents. That's something that I never do. And you know, I haven't chosen a problem yet, but we're going to pick one. And we're just going to figure out where is projectile motion. Okay, so we have physics, we have motion in 1 dimension. Projectile motion, okay, it's motion in 2 dimensions. I kind of remember that. So hell yeah, that's going to be chapter 4, page 71. And booyah. So let's go there. So we're just going to type in 71. And hell yeah, let's see if it actually brought it up to the right location. Yeah, sometimes it's, oh, you know what? It's page 71 in the book. We're at page 41, so we're just going to bust to page 71. Hell yeah, so we have motion in 2 dimensions. All right, booyah. And, I don't know, yeah, so this is an engineering textbook, so they're going to break everything down from kind of a differential equation. If they use this delta, that's going to be some sort of change in that variable. So this is a position variable, or like a position vector. And this delta, capital delta, this caret, you know what I mean, symbol, is going to be a change in that position. And it's going to be a substantial, it can be a substantial change, you know what I mean, some sort of visual change, where when we do the integration, we can take this change and just make it real small. That's where this becomes like a dr. You know what I mean, a derivative of that vector. So that just means that that change becomes infinitesimally small. Hell yeah. So let's just kind of see where they actually do a projectile problem. And, all right, hell yeah. That's why textbooks, I don't know, you have to dive in. I like these ski jump problems. But hell yeah, let's kind of bust to the end, and let's see which one. You know, they're all the same. I think I've done them before. But which one do we want to do? Ooh, this one is probably one of the trickiest. So, hell yeah. So let's see if we can do this one. This one is, you have a hemisphere, so it's like this is it'd be a half of a sphere. That's what this soccer player is standing on. And when you look at it from the side, we can see that it's just a half a circle. Okay, hell yeah. So let's read this one. I think this will be a good one. Whoop. So it says, this is 54. So it says and we can maybe get both in view. So a person standing at the top of a hemispherical rock of radius r, kicks a ball, cool, initially, and the ball's going to be initially at rest on top of the rock. So this is this is the rock. It's, you know, someone carved out a rock that's a half a sphere. Cool. And so the soccer ball is initially at rest on top of the rock, and the person is going to kick it and give it some sort of horizontal velocity. Now this is going to be a vector, you know what I mean? So anytime that I see a vector, I'm going to kind of slow down and be like, well, it has a magnitude and a direction. So what's its magnitude? I don't know, let's just guess. Well, let's just say it kicks at 10 meters per second, whatever. And then what direction is this soccer player going to kick it? Well, it looks like he's going to kick it totally horizontal, and we're going to call that the x direction. And this little I is for initial velocity. So that's what, hell yeah. So we have that vector. And don't be confused with this I, because we might say this x direction, you know what I mean, is a vector in the x direction could be like I hat, which is a unit vector in the x direction. Okay, well, let's see what it asks. It says, A, what must, and this is a red problem, you know what I mean, so I have no idea if I'd be able to solve this. But what must be its minimum initial speed if the ball is to never hit the rock after it is kicked? But when I do problems, we are going to guess. I think guessing is a pretty good way to do it. And so we're going to give, and the easiest way to guess is actually give this some dimension. And so we're going to do that. Okay, so there's a minimum speed if the ball never hits the rock. So the second you kick it, that's kind of fascinating too. Like, it's just like, what, it doesn't even hit once? You know what I mean? No. And so that's kind of interesting. And how the problem is laid out is I don't know how it's laid out. Anyway, we're gonna get to that. But there's all right, well, we're gonna get to that. So with this initial speed, how far from, so if we figure out what that speed is, that it doesn't hit the rock, well, how far away from, now that was my question, it's just like, well, what if it doesn't hit the rock and it lands right there? Is that possible? And we're gonna look into that. Hell yeah. But obviously not. I mean, if you're doing your intuition of reading problems, if it asks the question of like, hey, after you figure out what velocity of this soccer ball, where the soccer ball don't hit the rock, like how far away from the rock is it? That means that this soccer ball is going to take that path. And it means that the place where the soccer ball was going to hit was probably kind of somewhere in the middle. You know what I mean? Just visually, like maybe that's kind of sticking out, for lack of a better term. And that's all we have for this problem. You know what I mean? So we just have those things. Okay, hell yeah. And so how would we guess this? I have no idea. But one thing that we can do is give this thing dimension. And so, but what are we up against? You know what I mean? This is where I think people get into you get into tricky scenarios where they're just like, well, give me an equation. I need an equation. I need an equation to be able to plug in some numbers and get an answer. But with this I think you lose the actual relationship that's going on. The only reason things are, you know what I mean? And this is Newtonian, like Newton at its finest. Because we have a lot going on. From the physics perspective, I mean, we have a lot going on compared to, just like the first chapters, we just talk about like a particle, and then it's probably worse because you're just like, what the hell's that? And does a particle even have mass? And you can give it mass and stuff and all that. But anyway, so what we have here is this soccer ball for sure has mass. And for these projectile problems, we're actually going to treat this soccer ball as a particle. So, you know what I mean? We're just going to say it'd be the same as if you took a little chunk of neutron star, which is, like, all a neutron star is just neutrons packed like they would be in, like, where, you know how you have an atom with neutrons and protons, and, like, for whatever reason, they're just packed together? That's kind of what a neutron star is. It's like basically you just have that. You don't have this extra fluff of electrons. That's the density. You know what I mean? The packing together of neutrons and protons and stuff like that. But hell yeah, that would be the densest you can get something. And but booyah. So let's say you just have something like that. That's the size. That's the same mass as the soccer ball. So you can really visualize that this soccer ball is a total point particle. It doesn't even have to be a soccer ball. And for this problem, these are kind of interesting. It doesn't even have to. Well, the thing has to have mass. That's for sure. And that is probably the trickiest part. Is just like, well, why can this mass be actually anything? It doesn't even have to be the mass of the soccer ball. If this kid kicks a heavy rock from the top of this hemisphere, same initial velocity, you know what I mean? And so I'm trying to do these, like right now I went too hard on the math problems, so I kind of strained my thumb, you know what I mean? Like writing too much, it's crazy. So we're trying to do this with kind of minimal effort. I don't even want to break out these tools. I just kind of want to talk my way through that. So yeah, the first thing you would want to do is realize that you have, like in the equation that people don't use is the gravitational equation. And so let's not write it, let's just say it. The force of and what is the gravitational equation? It's Newton's law of gravitation. And I don't understand why you have Newton's 1 through 3 laws that come up. And then you just gloss over this fact that if you have a chunk of mass and it's next to another chunk of mass, then you're going to get some sort of attractive force between those, and that's going to be the attractive force of gravity. Now, is this soccer ball being attracted to this hemispherical rock? Sure, but that's not what we're talking about. That force is so small that it's neglected for this problem. But what this soccer ball with some sort of mass is next to is this huge Earth that appears to be a flat, it appears to be flat, but it's not. It's a huge ball, spherical ball. Anyway, bulged at the center. And so that's a hell of a lot of mass. And Newton's law of gravitation says that, well, hey, if I have a chunk of mass, this soccer ball, and then I have the Earth, which also has a huge amount of mass, there's going to be an attraction between, and then that's the other thing is like you would want to cluster the Earth as a point particle that's centered at its center. You know what I mean? If you don't want to do like the integration. I mean, because you have to treat the Earth as a bunch of particles, and then each of those particles, the particle over here has some sort of little attraction, and then the particle over here has some sort of little attraction. So what we should be doing, actually, it'd be kind of fascinating, I might look at that later tonight, is, integrate, say that, hey, I still have a little chunk of mass of Earth right there. This little chunk of mass, and look at this. This little chunk of mass is actually fairly close. You know what I mean? So this little chunk of mass is going to be more attracted than the chunk of mass on the other side of the Earth. But then when you integrate all that, you're basically saying, you know what I mean? It would be as if, that's what the integration kind of shows. It's not that this chunk of mass cancels with the chunk of mass that's on the other side of the Earth. It's just that they average out, and it's like both would be in the middle. You know what I mean? So that's kind of the easiest way to say it. And so what you get is just like, hey, you could take all the mass of the Earth and just, pretend like the Earth is a neutron star, and all this mass is in the middle, and then you have this. And I think this is really good for physics problems. Physics problems, it's really good to imagine, be able to concentrate the mass, but then just imagine all the mass of the Earth is so dense it's just right in the middle, and it's the size of a ping pong ball. But then we have made a substance that just weighs nothing. You know what I mean? Like even less than aerogel, or just think aerogel. And so you have this Earth made of aerogel, and then you set up this experiment where now you have this, and let's say this rock is made of aerogel too. So now what you have is a soccer ball with mass. There's no other mass anywhere else. Everything's made of aerogel, and for this scenario, it's going to be massless. And then you have the Earth that you've concentrated its mass down to a ping pong ball, and that's going to be located at the center. And just it's fascinating, because I'm so glad I'm doing this, because if you don't visualize that, then you're going to look at this problem and you'd be like, hey, I need an equation, give me the equation, and let me plug and chug. And it's just like, oh no. And then what I realized for all of these physics problems is, and even into sophomore year, even through junior year engineering, a lot of the problems you would just use mg. You know, you would use the gravitational constant g, and you would do mg. And I think that's a disservice. Like my thinking is like, I mean, sure, if you can use an equation to get the answer, it's great for tests. It's really good for like first practice. If someone's introducing a concept and be like, hey, I'm going to give you this equation, you know what I mean? Hey, let's do a quick proof just very fast. And then, but here's some problems that you could use with those equations, and all you have to do is just plug the numbers in, plug and chug. And you get the answer in the back of the book. You know what I mean? You get that endorphin rush. I think we all want that. But then at the end of the day, you get to a point where you're just like, well, it would be cooler is if I could actually understand what's going on. You know what I mean? And that's where if you go back to the proofs, I mean, that's where if we scrolled up, it looked too much. You know what I mean? Delta's this, and then, you know, and I don't even think they do a very good job of showing the integration. In most of these physics and engineering books, even the material mechanics books, is they'll show you the integral, but then for a lot of it, they'll just try to get the equation, you know, where it's just in more of a equation-based. They'll kind of skip the integration process. And that's a disservice as well. Because then you're just like, well, this equation works for this problem, but it's very specific, and I have to kind of remember why I'm using this equation for this type of problem. All right, hell yeah. So that's the first place that I start, is the fact that you actually have an Earth with mass. And, I mean, because if you do this, because that's the other thing. I mentioned Newton. Is just like, let's do this. And this is really helpful for free body diagrams. Because if I have this soccer ball, for a free body diagram, I always just pretend like the thing that I'm analyzing is in outer space. And so I'm going to take this soccer ball and just and pretend like it's not even in outer space, but it's the only thing in the universe. So let's say you have a universe that's just a total blank slate, you know, and then you can put this soccer ball in it, and then you have given it some sort of velocity, you know, in that direction, the horizontal direction. And guess what? If that's the only parameters, you know, in that scenario, that soccer ball is going to go into your fictitious universe with that velocity forever. And so that's one of the classic Newton laws. And I think you can visualize that if you actually take the moment and be like, hey, let's take this soccer ball and just wipe out everything and just pretend like it's the only thing in the universe. No stars, no nothing. We have a universe with that soccer ball. We give it some velocity. Hell yeah. And then that really drives in. It's just like, why would this soccer ball change? You know what I mean? Or, here's another thing. If I wanted to change that soccer ball's velocity, well, now I actually, that is a conundrum. If this soccer ball is the only thing in my fictitious universe and I give it some velocity, how the hell am I going to slow it down? Well, I mean, if this universe has the same properties as our universe, well, you're going to have to have another chunk of mass. Because, well, that's not true. But it brings up the idea of force. What the hell is force? You know what I mean? Well, from this easy physics perspective, we know that one way, and this is a very interesting, this is one of the more mysterious, you know, aspects of force, where, even Einstein was very fascinated with the fabric of the universe. How if you just have a chunk of mass in the universe, it has influence over every other chunk of mass. There is some sort of relationship between this chunk of mass and every other chunk of mass. Now, the magnitude of that relationship peters out. Doesn't peter out to zero. It's not a logarithmic. It's just a 1 divided by the square of the distance. And so if something, if you have two chunks of mass in the universe and you have some sort of attractive force, if you choose to move those 2 chunks at twice the distance, well, that attractive force is going to be a quarter. And then if you, and then if you actually doubled that distance, it would be, it wouldn't just go to a quarter to an eighth. It wouldn't just half. It would actually quarter. So it would be a quarter of a quarter. It'd be a 16th. And so that's, so it's just a square. So it for sure gets small fast. That's for sure. That's why we're not, when you jump up at high noon, the sun isn't levitating you. But technically it is. You're going to weigh less, and you should be able to jump higher playing a little b-ball at high noon than, at nighttime when both the sun and the moon aren't above you. You know what I mean? All right, hell yeah. So I think that's a pretty decent way to start this problem off. And it's always just good to kind of wrap your mind around. And then so let's go back to the soccer ball being the only thing in the universe, and we gave it some velocity. The other way to change its velocity is to, impact it with some other, soccer ball that's moving at it. And, if they both are moving at the same speed and they're the same mass, we hit them together, they do their thing, and let's say they rebound elastically. There's no energy lost, and all energy, because that's the other, the Newton says, hey, this is a chunk of mass, and, that is fascinating. Because if you think of this soccer ball as just maybe like one elemental chunk of mass, and I think that's very difficult because things definitely aren't more concrete when you break them down into smaller. If you just have one hydrogen atom with one proton, you still have an electron, and I think you almost dive into the quantum weirdness of location. It's really difficult to pin down location, and that's where I need to do some more quantum stuff, where it's just like you have properties of momentum and properties of location. You can know something's momentum, or you can know something's location. But those are, would you say they're inverse related? And it's kind of fascinating. That's the Heisenberg uncertainty principle. And even if you knew something's location to the most precise level, there's something interesting about that. Some limits. There's some limits on what you can know. Anyway, but even if we just have 2 elemental chunks of mass and they hit each other at the same velocity, they for sure are going to I don't know. There's no way they could stick together if nothing else happened. The only way 2 things can stick together is if they transfer all that energy to internal energy. You know what I mean? And then that's kind of interesting. That kind of brings up the energy can't be created or destroyed, is that if I have a chunk of mass flying across the universe this way, and it hits another chunk of mass, the only thing that can happen is that they elastically collide and then rebound at the same velocities. If there is no other, and then that brings up because even with this problem, we have a collection of particles. This soccer ball is made up of a collection of particles, and so if we're talking about rigid bodies, we maybe want to think of this soccer ball as a rigid body. What that means is that when we kick it, it doesn't change shape, and we even know that's not true. You know what I mean? And so that's kind of fascinating that even in this problem, the soccer ball is going to be deformed. But anyway, where do we want to go from here? Oh, yeah. So if two soccer balls collide with each other in our fictitious universe, then, they're made up of a bunch of molecules. We know they can deform. And then we also know those molecules can pick up heat. And this is where, I would love to study thermodynamics just from my perspective, because I swear I went through thermodynamics and it didn't feel like physics. It felt like a weird, I don't know, it just felt weird. It felt like a weird class where it's just like Newton's king, and it's just everything can go back to Newton. And the fact that all heat is just a measure of the movement of particles. And so hopefully I did a good job of saying if I only had one particle in the universe and it's traveling with a constant velocity, you ain't changing that particle's velocity unless you actually introduce some other mass, or that's one way. That's the other thing, is that other things can influence mass. You know what I mean? Even photons can have an influence on mass. But just from a classical, and especially for this book, you know what I mean? I think it's useful to know that, I think that's, let's see, energy. Yeah, I think that's still useful, is that something's energy is just the amount of mass that it has and its movement, or its potential for movement. So even if you had a dam filled up with water, that's a bunch of mass, and its potential, it can potentially move. You know what I mean? You can unleash the gates, and then you can use that moving mass for other things. And I think that's very useful for this, because life is a big Rube Goldberg, you know what I mean, when it comes to just mass and motion. And I think from this physics book, since this is introductory, from a classical perspective, where you're not having to get into, you know what I mean, things that are massless, like light and stuff, and their interaction with mass, I think that's a pretty good definition. You can just pretend until you get into higher levels of physics. You can kind of just, in my mind, I do it all the time. It's just, especially if we're just talking classical stuff, thermodynamics is just classical, where it's just what are you talking about with heat? Heat is just movement of electrons. And so that's where, even some of the professors at some of the bigger universities, the physics professors, they'll talk about the jiggliness. Even Feynman, he'd be like, everything's jiggly. You know what I mean? And it's just hell yeah. I don't think you can technically call yourself a physics professor if you've never used the word jiggly. You know what I mean? Because, hell yeah. So even though this soccer ball is a bunch of mass particles, they're still jiggly. You know what I mean? It's a rigid body, but we obviously know you can kick it and it can deform anyway. But also it's jiggly. And so, if two soccer balls collide together, and let's say they're just totally rigid, they don't deform. We made two soccer balls that don't deform. Made out of, excuse me, oh shoot, I'm gonna run out of voice. Yeah, let's get some ice water. All right, hell yeah. So we're back. We got some ice water. And, all right, where do we want to go from this? Oh, yes, I do want to talk about that heat thing. Because, yeah, if these two steel soccer balls hit each other, and let's say they don't bounce back, with the same velocity. The only way they can't bounce back with the same velocity is if other mass is also moving. And we have to bring in the term acceleration, because that's what Newton found, is that force is equal to mass times acceleration. And that means that, so there's three parameters there. You have a force on one side, the equal sign, and then a mass and acceleration. And so, but that equation for sure has an identified mass. And so I always circle that M. And so we can circle this soccer ball. This soccer ball has a mass. Now, in our colliding soccer balls, what we're going to say is that the soccer ball changed velocity. And so that's acceleration. The definition of acceleration is change in velocity. It's in some sort of calculated time, so it's change in velocity divided by change in time. All right, cool. But and that equation basically says that's the only way that you're going to get some sort of mass to actually change velocity. You have to apply a known force. And so, yeah, in the universe, you have to identify what is like a, well, and that is, it's kind of like a, I think F equals ma is almost a tautology as well. It's just like, well, what the hell what are you calling a force? Well, a force is just, something that makes a mass change its velocity. So if you can go out into the universe and find things that make mass change velocity, then you're a force. You've identified a force. So it could literally be photons. Photons might make, atmospheric air particles move. And so then you've identified a force. And so so even at the higher level physics stuff, or just the not so obvious, you're still trying to figure out what is making mass change velocity. And if you can identify what is making mass change velocity, then you can identify what is the force, like what is causing the force. Cool. And then back to this, it's because gravity is very kind of mysterious. It's like just the fact that you have mass next to other mass, you have some sort of interaction between them. And I think that is pretty decent of Einstein to do the whole kind of fabric demonstration. I don't know. This is like where you have like the rubber universe surface and the different weighted objects, and how it kind of curves. I think that's I don't know. Is that the best we can do? It doesn't seem... Anyway, so hell yeah, just the fact that two chunks of mass are just sitting there in the universe, we are going to get a change in velocity between two things. Now, in later chapters, I don't think this is like... Because even this year I was just like, well, we're obviously falling towards the sun. The sun's a bigger chunk of mass. We're a chunk of mass. And there's going to be attractive force between us and the sun. It's only a matter of time. I've heard in books that we're going to get engulfed by the sun, maybe in a few billion years. I have no idea how long that is, but it must be because of this gravity thing. And no, that's not even true at all. It's just really fascinating that all of the attractive force between the Earth and the sun is just to hold us into orbit. And it's just really fascinating. If that attractive force wasn't there, we'd be saying sayonara sun. And that is what's happening, honestly, because the sun is losing mass, and we're going to be, if the sun just lops off half of its mass or just disappears half of its mass, it would feel like we'd be like, whoa, like we're not attracted to that thing no more, and then we're just gonna peace out. You know what I mean? That would be an interesting... I really do need to do more of the physics problems when it comes to... I've left the exit velocity one because I think I would be able to just deduce that, prove it. I should be able to prove exit velocity just from my knowledge of physics, my knowledge of mass, force, and in the fact that something in orbit is it still requires, well, ooh, yeah, we got two different things here. Yeah, so if the sun is rotating around the Earth, the Earth is rotating around the sun. So if the Earth is just rotating around, the sun's way out here, the Earth is going this way. From that Newtonian perspective, if we just say the Earth is the only thing in the universe and it has a velocity that way, well, it just wants to go that way. Cool. So that's how you can make problems simple. This is the easiest way to make problems simple that I can think of. And it really helps you understand free body diagrams. Gonna get some more ice water. Because a free body diagram, what you're going to do is you're going to draw the Earth like on your page, and that's supposed to represent a free body diagram. And then you're supposed to draw arrows on it representing force. And no one knows what the hell's going on. So one way that's just very useful is just to imagine the Earth is the only thing in the universe. And now what do we? And then we're going to go back, and then I'm gonna treat it like a light switch, where you have two things going on. One is the Earth is the only thing in the universe, and then you're going to flip the light switch, and then the Earth is now where it's positioned, and then the sun is over there, and that's kind of what you're analyzing. All right, let's flip the light switch again. We're going to analyze the Earth being the only thing in the universe. We're going to, damn, it is sucky. But anyway, flip the light switch again, and then in our current scenario, the Earth has a velocity. Cool, light switch. I hate this. Anyway, so you can, if the Earth is the only thing in the universe and we give it some sort of velocity that way, it's going to travel that way for days, forever. It's the only thing in the universe and it's a mass and you gave it velocity. We have just shown that the only thing that can actually change its velocity is, a lot of things could. But those are physical properties that we have to discover. And one is having some sort of other mass in the universe. So that's what we're, And then so let's say we do have this Earth and it's got some velocity that way. Like, what's one thing that we would maybe want to do? Let's try to bring it to a stop. Well, that means that we have to put a force on it in that direction, and a force in that direction on a mass will change its velocity over a change in time. That's F equals ma. That's the relationship that Newton discovered. But now I think this is the tricky thing, is that let's say this Earth is just going this direction at a constant speed, and then all of a sudden it just changes direction. And it's still going at that same speed. Like, what do you think about that? Because if you just asked an engineer student in this course, freshman year, it'd be like, get out of here. You know what I mean? Like, I'm trying to do my problems. I got my equations. I got my unknowns. I got my answers in the back of the book. I'm trying to get that endorphin rush. But that's it. You know what I mean? So if you like that, so this is kind of the one that I've been using, and this is, I don't think this is simple, because this is why people are just like, hey, can you do more about calculus? Can you do more about this? So this concept just relates vectors. It relates that velocity is a vector, and so if I have a velocity in this direction, cool. What I do not have is any velocity perpendicular, and the perpendicular component is 0. And what we know about vectors is that we can, they don't even have to be perpendicular, but we can just add vectors using the parallelogram method, usually just tail to tip, and then tail to tip, and then connect the first tail to the last tip. And that's going to be vector addition. Cool. If I have a vector this way and a vector component this way, I'm going to box it in and then draw the resultant perpendicular. It'd be the same thing as taking this vector and then this one, And then you can also go the other direction. I can do this one first and that one. So that's kind of the parallelogram, because you can do it as a parallelogram, or you can do it even as a square. If we get our components down to like, hey, this is going to be the x direction, this is the y direction, so that's what we do there. And so if the Earth is just going in this direction, what it does not have, it has 0 component in this perpendicular direction. And so if we just say that this Earth is going this way and then all of a sudden kind of makes a turn and continues with the same velocity, well, now, two things happened. It's a tricky one because it looks like, well, you're just going the same velocity, so nothing happened. Well, 2 things happened. Let's just take this component. So, and let's say we're going to go this way, and then we're going to change our speed we're going to do a 45-degree angle. And so if we look at this 45-degree angle, we can break this velocity vector into 2 components. And thank you for not letting me draw, because it just, like my hand, I can do this almost left-handed, tell you. I need to heal my hand. And so at a 45, that Earth's velocity has 2 components, one in the x direction and then one in the y direction. And so let's say the Earth's velocity is just 100 whatevers, meters per second, who cares? And when we do vectors, I like to use 100 because maybe you can consider that, because we're dealing with right triangles. So if this is the 45 degree, I can do its component this way. And if I did a right triangle here and then here, if I did the parallelogram method, I'm going to go this way or that way, or I'm going to go this way or that way. They're 2 similar right triangles. And what we say is the sides of these triangles are going to be less than the actual. And that's the cool thing about vectors, is it's usually the vector is the hypotenuse, and then you want to know the components. The hypotenuse is always the bigger number. We're going to say it's 100. So therefore, the components are going to be less than 100. And that kind of brings up sines and cosines as being percentages of the hypotenuse. If we have a 45, it's good to remember square root 2 divided by 2 is 0.707. And that's very accurate, because I think it's like 0.707. It could be 0.1 or 0.7071, but it's really accurate to 3 decimals. And how you can get 0.707, you can just think 007 in a weird way maybe. But square root 2 is 0.1412. What am I saying? Is 0.1414. Is it 0.1414? Yeah, it's sorry. Yeah, square root 2 is 1.414. And then sure, there's a 2 in there. Yeah. So, but if you think of square root 2 as just 1414, 1414, 1.414. Then if you half that, you're going to, half of 14 is 7, the other half of 14 is 7, and you get 0.707. So it's really easy to do that. And if you know square root 2 is 0.14142, then you know that, then you even say that's 0.7071. And we have even to 4 decimals, but I don't try to memorize that. I just memorize it to 3 decimals and then have some sort of reasoning. Hell yeah. And then so 0.707, that's synonymous with 70.7%. So if this is our velocity vector of 100, this component is going to be 70.7% of that, and its actual component is going to be 70.7 meters per second. And this component is going to be 70.7 meters per second. Because we can treat velocity as vectors, what we can say is that the Earth did have a velocity of 100. And now in this component, it reduced to 70, basically. It went from 100 to 70. So now the only way for that to happen is, that's a change in velocity. So we had to, that is definitionally, we had to have some sort of acceleration. And if we had acceleration due to Newton's equation, F equals ma, there had to have been a force. You know what I mean? Whatever that means to you, or to figure out what causes forces in the universe. And all a force is, it's a tautology. It's just saying that if we can have a mass and I can see a mass change velocity, I'm going to call whatever caused that mass to change velocity in a chunk of time. That's acceleration. Change of velocity in a period of time, divided by a period of time. That's what we're calling a force. And so that is kind of why it is kind of, it feels like I'm not going to use the word tautology again because I feel like I'm not using it in the right way. But, yeah, it's just definitionally one is equal to the other. Force is just, yeah, isn't that weird? It's kind of fascinating. It's like, why do you even need the equal sign if you're, you know what I mean? That's tripping me out right now. If, hell yeah. I guess it's like, if you have the ingredients, I always like try to do this, probably weird, but maybe it's not if we just make it American. Apple pie is American, you know what I mean? And so if you have the ingredients for the apple pie over here, that's just the ingredients. Like you divvied up everything in little dishes like they do on the Food Network. And then over here is that you hours later you actually have the full apple pie cooked. And you can say that those are both equal. You know what I mean? But like obviously one's the ingredients and two is the actual thing that you're going to eat. So yeah, so I think I hate analogies, but anyway, so I think it's similar to that, F equals ma. How they're equal. Anyway, what are we talking about? No, I think we're doing good. And for whatever reason, like I feel like everything else gets said. People are doing, it's like, oh, I don't know how to do this problem. What equations do I do? And where's my unknowns and stuff like that. Who cares? You know what I mean? Because there's going to be a question after question that you're not going to know. Every question that I look at is just like, I don't know. Who knows how to do this? And even if you're able to do that one, you can just pick up another question and you're going to be like, damn it. I don't think I'm any faster at answering this. So it's just interesting how, like, this is what I want to share, I guess. I don't know. So F equals ma. Yeah, oh yeah, the Earth going this way, and then it changed its direction. So we had to have some sort of force because we've identified some sort of deceleration. It's an acceleration in that direction, it's slowing down. And then we said that this Earth had velocity this way. It had no component that way, but then the second it made this corner, now we picked up all this change. And so, and we had to have some sort of force to do that. And the only thing that's not correct with this analogy is that you can't have an abrupt change in direction. It has to be a differential change in direction. You can have abrupt change in acceleration. Your acceleration can be abrupt. Be like, right now I'm going to switch from constant speed to I'm going to hook this thing up to a force, like start a little jetpack, start a little rocket, to slow it down and stuff. Which all a rocket is just chunks of mass flying the other way that are colliding, you're impacting, so it's just interesting. It's like that's a very classical thing. Is that, hey, if we want, we know mass is in motion. If we want to utilize that motion, we're going to, even from the chemistry perspective. That's why I don't like the terms energy, because it's just like you're making it one more level of confusing, even though like the math gets easier when we talk about energy and energy equations. The understanding just goes out the window. It's like, what the hell are we even talking about no more? That's where it's just like mass and velocity. I kind of like it. And change in velocity, obviously. Mass and acceleration. All right, hell yeah. So that's the Earth example of it changing direction, and it required a force to do so. That force was this direction, and that force was down, it was up. To get it to go that direction, we had to have a force up, and then to get it to slow down, we had a force that way. And those are equal. So in this little scenario, that force is going to be like at a 45 that way. Cool. And what we, let's see. And yeah, when something goes around, like the Earth is going around the sun. Oh, that's interesting in that scenario. Oh, yeah. So in that scenario, we had this 45-degree angle, and we're slowing down this direction, and we're speeding up that way, and then our resultant is going to be at a 45 that way. And then if we did it again, so let's say we did a 45 to the Earth, and then another 45 is going to be this way. So it slowed down this way, and then it actually sped up this way. Is that right? Because we were going this way at 70 and 70. Now we're not going this way at all. So we're going to slow down 70, and then we're actually going to speed up. We didn't speed up 70. We just went back to 1. And so that velocity vector is going to be hella this way, but then just this way just a little bit. So that velocity vector is going to be that way. But if we don't just do big 45-degree changes in angle, if we just say, hey, the Earth is going to go this way and it's just going to change 1 degree. Okay, cool. Then its velocity vector this way hardly changed, but we actually did pick up. That's the deal with small angles. If I have a triangle that's a small angle, here's the triangle with the small angle. Its component this way, like literally, is the same as if the triangle was a total straight line. Of that length. But if we make that triangle just a little bit of angle, this component hardly changes, but this component actually is substantial. Even with small angle triangles, this component is substantial. That's the one thing to be aware of. If I even have like a couple degrees, this can be percentages, in magnitude. And so that's what we have, and that's the direction that we have. And if we bring this triangle down, if the Earth is just hardly, a fraction of a degree change in angle, cool. This component did not change this horizontal component, so it didn't require any force this way because we didn't have any change in velocity that way. But like I said, with these small angles, that's going to be very crucial information for engineering. It's just like if I do have a small angle, I think the most important thing about that small angle is that even though it's a small angle, I think people just lose their brain when they're just, okay, I have a triangle with a small angle. Everything's small, it feels like. But this is still substantial. And so that component is percentagely, I'm just going to make up words, but that is a very substantial component. And so in this scenario, we are going to have a change in velocity that way that's substantial. And so our arrow is going to be pointed that way. And now we have this new, and so that's the direction that it, and then so this is our arrow, this is our velocity. Our velocity is a vector that's going to be, I'm just going to say it's this length. And the length from there to there is going to be proportional to what that velocity, the actual velocity is. But we did change a little bit of direction. Look at this. So even just visually, let's say this is 100, and then I have this small change in angle. What do you think this is? It could be as much as 20, at least 15, and that's substantial. Now, this length right here, how much did it shorten? Because it actually shortened. If I take this length up, pivot it from here, it's going to go an arc, and so it is going to be slightly shorter, but it's imperceptibly shorter. In that direction hardly changed. We did slow down a bit, but as this triangle goes to be a smaller and smaller triangle, that change will be 0. But this will still have a change. So that's perpendicular, and that's what we call the normal. And this will be directed right at the sun. So if the Earth changes just a little bit, this change in velocity is an acceleration, because that change in velocity have to happen over a change in time. That's a classical thing, where it's just like, hey, if I observe a change in velocity, time had to have been, involved. We're not talking about... Well, the quantum gets into stuff that can do things without time. It's kind of fascinating. All right, but cool. And we're going to pick up that acceleration is going to be in that direction, and that's going to point right towards the sun. That's perpendicular. And then the next component is going to be at this new slight angle, and we're going to say that, because this thing came in, it changed this angle, and now we're going to say it changed the angle, that same angle again. So now it's going to be up here. This length in this direction hardly changed, but we have the changes for sure this direction. And we're going to have to rotate our coordinate system, because now we're just talking about a change in this direction and perpendicular. So horizontal, perpendicular, this is going to be tangential to the Earth's rotation, and this is going to be perpendicular. All right, hell yeah. And so that requires a force. So all of this was just to show you that if the Earth rotates around the sun, that every time it changes direction, that required a force. Like the sun the Earth just wants to just chill. It just wants to go straight into oblivion. But something's helping it out and is putting a force on it. And all that force is just using it to change its velocity towards the sun. And that's what our orbit is. Our orbit is the balance point of that change in velocity, because we don't have any velocity component. At any given second, we have 0 velocity component towards the sun. It is completely tangential. But in that 1 second, the sun's like, come here. You know what I mean? Because we're a chunk of mass, and they're putting a force on us. And then we're just like, well, I didn't have any velocity towards you, but I guess I do now. And that's a small angle, but that's substantial. Okay, and now after that second, I'm still just like, hey, dude, I'm chill. I just want to go into oblivion. And the Earth's like, no way, dude. We got a lot of nuclear mass for decades. Billions of years. So we're just going to give you some more force. And you're like, okay. I didn't have any velocity towards you, but now I guess I got a little change in velocity towards you. And in that second, you're going to be like, whoop, going towards you just a little bit. And but that component is just a vector component. So I was going like this direction, and now I'm going this direction. I'm still not going towards the sun. You know what I mean? Like, the sun's not just being like, hey, you know what I mean? Because I'm just like, well, I'm going this way. But the sun says, I'm just going to have a little component that way. And then as I do this, it's just like, now I want to just peace out. It's just like, hey, sun, see you later. But the sun's like, no, I still have nuclear energy for days in the form of mass and atoms and neutrons, which due to Einstein, those bend the fabric of the universe. And thanks to the inventors of rubber surfaces, we can show that with bowling balls and other small little round objects. And hell yeah. And so cool. So that's groundbreaking to me. I think last year I did not realize that all the attractive force between the sun and the earth due to gravity is just to keep us from not peacing out. And it's a balance point. It's kind of fascinating because why is it a balance point? Well, one is it's not very strong. So like we're not just getting sucked into the sun. And like at any given moment, we just actually want to be farther away from the sun. But the sun's like, nah, I actually got quite a bit of force. But you're pretty far away anyway. And so, yes, I can't really explain why it's a balance point. Because it seems like if we... I don't know. Like, let's say some external force takes the Earth and puts it farther away from the sun. Okay, now do we escape the sun? You know what I mean? Because, like, we have less force on us. Oh, yeah, but our circle is bigger. And then even our, and it depends on our speed as well. Yeah, it's kind of fascinating. So speed and the circle that we're traveling. Because, well, and I wouldn't say the circle, because if you look at it at a moment-to-moment basis, we're not traveling in a circle. We're literally being like, see ya, sun, I'm just going to just go into oblivion this way. And then the sun's like, no, I'm going to change your velocity towards me, which you weren't going towards me. So the perpendicular component, the sun's like, hell yeah, you're actually going to have a little velocity component towards me. So let's say I'm out here, and but yes, like, would I slow down? That's kind of a fascinating thing. Oh, yeah. And the whole idea of a, I don't know, I'll have to think about that one. Because I think you can still look at the sun is like the Earth where we're falling towards it. You know what I mean? So we're picking up speed as we're, yeah. But we're not picking up speed in our trajectory. Because that change in velocity is just perpendicular. There is no change in velocity in the direction that we're actually going. But that is because we've reached equilibrium. Like, if an asteroid is actually just heading towards the sun, and, you know what I mean, just directly, well, the sun's like, hell yeah, like, come on. And then I'm just going to keep pulling you in. But everything's kind of moving. I think we're done with planet physics. Holy hell. All right, but gravitational, the equation, Newton's law of gravitation, it says that this is a chunk of mass, the Earth is underneath us, there's going to be an attractive force between them. And again, what the hell is force? Well, force is equal to mass times acceleration. It just means that, like those two things, if we do have a mass, we are going to observe an acceleration. I guess you could also say, like, well, if the soccer ball is just on the Earth, why isn't it accelerating? It's because we can have other forces. You know what I mean? One force is just the soccer ball is just hovering in air and the Earth is below us. That is gravitational force. That's it. If we draw the free body diagram, we draw the soccer ball, and there's a force on it, you know, getting pulled towards the Earth. And actually, the Earth is actually getting pulled towards it, but not at the same speed. Well, I mean, I guess relatively at the same speed. But the center of mass of the... if two objects are actually colliding towards each other under gravity, the center of mass won't change. If that's the only thing, if you just have two objects, the Earth and then a soccer ball, and that's your universe, and there's just going to be a linear attraction between them, the center of mass of that system does not change while the soccer ball is moving towards the Earth. So as the Earth is moving towards the soccer ball, the soccer ball moving towards the Earth is also moving slightly towards the soccer ball. But because the mass of the Earth is so huge, the center of mass of the system is very, very close to the center of the Earth, and pretty much will, doesn't really matter what the soccer ball does at all. The center of mass basically hardly changes, so therefore the Earth hardly changes, but it does change, you know what I mean? And classically, it for sure definitely changes. So if you drop a soccer ball, even from, chest height, drop it on the ground, the Earth moves up towards the soccer ball, keeping the center of mass of the Earth and soccer ball at the same location. Therefore, the soccer ball doesn't just fall down towards the Earth, because now that center of mass would be you know, it would be different now. If you're having a soccer ball at chest level, the center of mass of the Earth in soccer ball is a little bit higher than the center of the Earth. If the soccer ball hits the Earth, you know what I mean? You could say the soccer ball and the Earth has a center of mass that's basically in the center of the Earth. But prior, it was just a little bit higher. All right, so all right, hell yeah. And so for Newton's law of gravitation, that equation, that's the only thing I'm going to write. So we have the force, because it is going to wickedly destroy my hand if I do more. The force of gravity is this gravitational constant. We're going to do mass of the soccer ball, mass of the Earth. You can put a little e here. And then divided by the radius. It's just, you could say x squared. It's just the distance. And where is it? You know what I mean? Hey, it's the center of this one, and it's the center of that one. So hell yeah. And we're just going to say that's r squared, and this is the radius of the Earth. The only reason it's the radius of the Earth is because the Earth is so big. And I do this one as an analogy. You could be on top of Everest, or just in the ocean, or in like the trench, or whatever. This distance doesn't really matter, because the Earth's radius, it doesn't matter if you're here or here. If I do my problems where I just come to the, you know, whatever the ocean level is, and the radius of the Earth is, there's a lot of sixes in these. We're not going to get into that. And so who cares what it is? It's 6 million meters. It's 6.7. I think it's 6. Is it 6.2? I think it's 6.27. I think there's a 7 in. That's the bummer about memorizing numbers. So I think there's a 7 in there. But it's not 6.7, because if it was 6.7, I would say I would round to 7. But you know what? I think it's 6.37. And, well, yeah. And it's weird, because it's 6.37 times 10 to the 6. And so even though it's 6 times 10 to the 6, that you could round that to 7 times 10 to the 6. So this is 7 million meters. No, is it? It's 6 million meters. Oh, I apologize. I'm not just rounding. I'm not rounding this to 7 times 10 to the 6. I'm rounding this 6 up to 10. I could say this is 10 times 10 to the 6, which is, sorry about that, that's going to be 1 times 10 to the 7. So I could say that 6 million meters, or it's 10 million meters. You know what I mean? There's two different ways to guess. You should always be doing that. You know what I mean? Don't just memorize. Or if you do, if you memorize 6 million, that's pretty good. If you try to do like me and do like 6.37 and try to memorize that, but then forget whether it's 6.27 or 6.37, but it's probably 6.37. But then also just have crap guesses that are just actually make the math easier, and be like, well, 6 rounds up to 10. And 10 times 10 to the 6 is 10 to the 7. That's 7 million. 7 million meters. All right, hell yeah. But this is the equation, gravitational constant, that you get just mg. And why do you get mg? Well, this is 6. It's 6.66. I do like the devil on that one, because it's like 6.66, and people are like, whoa, physics, devil. And then that's going to be 10 to the negative 11. That one's hard to memorize, but there's going to be 6's galore. Mass of the Earth is 6. But it's 6 times 10 to the 24. That's another one that's just like, well, that's not a 6. But then the radius of the Earth is 6 times 6. I mean, it's 6 times 10 to the 6. And then we're squaring it. So when we square the 6 times 10 to the 6, we get 6 times 6. And then we get 10 to the 12. This 10 to the negative 11 comes downstairs as 10 to the negative 11. And so now, just a positive 10 to the 11 downstairs. So now we have 10 to the 23. And then the mass of the Earth is 10 to the 24. So 10 to the 24 divided by 10 to the 23 is 10. And hell yeah. So those three numbers turn out to be 10. That's it. You know what I mean? And so now you have the force of gravity is equal to the mass that you're analyzing, the soccer ball, times 10. And what does this mean? It means that if I have the Earth, and here's the soccer ball, and here's a cliff, and I drop the soccer ball, there's going to be a force on that soccer ball of this gravity that's just the mass of that soccer ball times 10. And 10 is what we call G. But that's disservice by saying force of gravity is mg. I think it is. I think if you're not doing this every time, then you're just... I think that this was the one where it's just... There's plenty of equations where you're just like, give me the damn equation. But this one is just like, you can go your entire career in engineering. And I just realized this in textbooks, because even in textbooks, they're going to spend like one line on gravitational equation, Newton's law of gravitation, and they're just going to derive the force of gravity as mg. But this is only for things at the surface. But like I said, it doesn't matter if you're in a trench or on top of Everest. Everything in that zone, which that's all of life. I mean, unless you're doing really cool things and getting up to the station or even farther away. Yeah, that's where we live. That's kind of claustrophobic. That's like one thing that's just like, oh yeah. Even just going out and outside and being like, I can only see 20 miles in all directions, and the Earth feels like I'm in the Truman Show. But yeah, just the fact that we are just, there's plenty to explore, plenty to do, but we are, that's our zone. You know what I mean? That's our zone. F equals mg, unless you're needing to, but yeah, you should always be able to drive this. Anyway, we're done with drawing. All right, hell yeah, I think we're doing pretty good. Maybe do a little 3-hour video. All right, so now we're going back to how do we guess this? Because, and what I just drove is all we need to know. I said 10 what? Well, for the units on that are 10 meters per second. And this the accelerator. What is G? F equals the force of gravity is equal to the mass of the soccer ball times 10. And 10 is... Oh, we got to draw that because that's the crazy thing. So you have this force is equal to mass times acceleration. And for a particle, I'm just going to say we have one particle. That's the soccer ball. It's one particle. And I'm gonna ask the question, hey, is there any forces on it? And we're going to be like, hell yeah, there is. And over here, I'm going to be like, well, what's the number of that force? You know what I mean? And that's where it's just like, well, we just derived it. We have a force of gravity is equal to mg. And so don't we get a number there? Hell yeah. And we do. And that's where it's just, that's where this actually sucks, I think. Because the units on this are the same as the units on that, but that's what the equal sign means. Is like they would have to be the same units, right? But we're trying to equivocate something that's not, I mean, we're not just saying one thing is identical to the other, but F equals ma says this is the mass we're analyzing, and I want to know its acceleration. And then so I say, hey, do we have any forces on this? And we know that gravity is a force, but this is more from experiment. I say, hey, let's set up the Earth, and let's set up a soccer ball. And then what I'm going to witness is I'm going to document the acceleration. If I can figure out the acceleration of this mass, and then let's take another mass that's like twice as heavy. And then I'm going to be like, ooh, that acceleration was the same. Okay, so I think I'm doing it in reverse. Oh yeah, do it in reverse would be like, hey, this is the experiment, this is your mass, and then we're going to observe an acceleration. We observe that the acceleration is 10 in both cases. And so, but what we know, so yeah, that's fascinating. But what we know is that if I have a chunk of mass and I just made the universe, and it has some sort of velocity, this is the only thing in the universe, and we got this velocity. The only way to change its velocity is by applying a force. And so this experiment that I did, here is like, hey, I have these objects with velocity of 0. And then maybe 1 second later, now they got a velocity of 10. And then my time was 1 second. So that's what we have. And if I said my time was 0.5 seconds, I would get a velocity of 5. And so I can actually see that's a linear relationship. And so we're, I don't know, you know what I mean? It's kind of fascinating. But yeah, so this is kind of the experimental side. And so if I did an experiment on gravity, I could say this is my mass, this is my acceleration, and why do we know that there needs to be a force? This is where it gets this is the stuff that gets me headed out, because it seems like a tautology. It's just like, well, what are you talking about a force? I mean, are you saying that if I have an Earth and then I have a relationship between the Earth where mass changes velocity in a change in time, that we're calling that a force? Cool. Yeah. So yeah, it's very fascinating. Okay. I'm striking out. I strike out all the time on that. I'm sure there's a way to explain it that your brain doesn't fry. But here's your equation. Here's the soccer ball. And then here's the forces. And I'd be like, oh, I have a force of gravity. And guess what the force of gravity is? That's why I don't like this one either, because it's mg. And so I'm going to put mg in this side. And that's going to equal ma. And it feels like my brain just exploded. So here's the soccer ball. The force on it is a function of the soccer ball, but this is due to the location of the soccer ball on the Earth and its radius, and now I can figure out what the acceleration is. But because these are just, almost identical equations, I can either cancel the mass or take this mass and divide it over here. It cancels, and the acceleration is just g. The acceleration is 10, but this is the acceleration of this mass. So I have a mass, and I want to know its acceleration. And I ask the question, is there any forces on this mass? And when the soccer ball's on the ground, why isn't it moving? Because, like, hey, didn't I identify, isn't there still the force of gravity? Sure, we still have mg on this side, but what we witness is it's not moving. So if this side is 0, because the acceleration is 0, this side has to be 0. So I have to have some sort of negative mg plus mg. I have to have the equal and opposite thing. And then also what I hate about physics is they give this the letter n, and they call it a normal force. And I don't know. I think that's the biggest disservice to physics. I hate the normal force. I think just the word normal, I mean, if it was so normal, it wouldn't cause any confusion whatsoever. But the fact that the normal force actually is one of the more confusing forces, especially when learning free body diagrams, I despise the normal force. Hell yeah. But that's your normal force. You know what I mean? That's just saying from a Newtonian perspective that this is the chunk of mass. And when I have this scenario, with the soccer ball on Earth, I can do the same thing as just like, hey, let's take that soccer ball and have it be the only thing in the universe. And then I'm going to go back to this drawing and be like, do I know there's a force on it? Hell yeah. There's going to be a force of gravity. I know that for sure, experimentally. But then it's not moving. And so if there's this force down, there has to be an equal and opposite force up. And so that was also kind of Newton's exploration, was just like, if something is stationary, 0 velocity, but I know there's a known force, there has to be an equal known force in the other direction that's equal. If there was an unbalanced of forces, then we would see some movement in those directions. And might as well talk about how if I have a force this direction and then I have a force down this direction, hey, these are equal and opposite, but they're not in line. And so even though this thing will not travel that direction, it's going to hella spin. And that's what's going to happen. All right, so where are we at now on this problem? I wanted to try to guess this one. I don't know if that's possible. But what we know about acceleration is it's going to be 10 meters per second per 1 second. So that's the units on acceleration. I'm going to have a change in velocity. That means I started at 0 and then I got up to 10. The crazy thing about this is I did not travel 10 meters per second the entire second. If something is falling towards the earth, like if this soccer ball just dropped off a cliff, it starts at 0, and then after 1 second it gets up to 10, and it happens linearly. I'm not going to get into the differentiation, but you have acceleration is the second derivative of position, and then you would write it like this, and that's like, why do you write it like that? Anyway, I'm not going to get into that. Because I don't know. No, it's just like, I just don't want to go down a rabbit hole. Because, yeah, I would struggle at that. Hell yeah. I hated differential equations. I'd never understood differential equations, and now I'm kind of understanding it, and then I'm trying to figure out why, why wasn't it taught in an easier way? Anyway, so at 0 velocity and then 10, and this is increasing linearly. And so what we can say is the average velocity is going to be 5. And I have an average velocity of 5 meters per second for 1 second. That is the one scenario that I always do in my head. Falling objects, 0, 10, average is 5. I'm having an average velocity of 5 meters per second for a second. In that case, I went 5 meters. If someone says, hey, could you go 5 meters a second? And I'm going to see how long, how far you go in that 1 second. You're going to go 5 meters. So, so I guess I could make this radius 5 meters. That's what I was thinking. And the other thing with vectors, because velocity is a vector, and if I said, if I have an object that has a velocity that way, it's just going to keep going that way. I think we drilled that in. And if something changes its velocity this way, cool. Like the Earth is getting pulled towards the sun but the Earth still just wants to go perpendicular and be like, I'm out of here. But if something changes the velocity this direction, cool. Now we got a little velocity that direction. And for gravity, that's going to happen every second. We're just going to keep increasing that velocity that way, and that velocity vector is going to grow, and it's going to grow. This direction is going to stay the exact same because there's no forces on that mass, and there's nothing that's going to slow it down. So therefore, if we kick this soccer ball this way, it's going to remain going that way and neglecting air resistance. And why would air resistance slow it down? Because you have this chunk of air. There's a little chunk of air, and it has a mass. And what did you do to it? The soccer ball hit it, and then it bounced it out of the way. This air molecule didn't do nothing to you. It has 0 velocity. The second it runs into this soccer ball, maybe it gets squished sideways, and now we have some sort of air molecule going hella fast. And the only way to take, and an air molecule does have mass, and the only way to take a mass from 0 velocity up to getting squished away, you know what I mean, and that's going to be some sort of number, is it required a force to do that. If it required a force to do that, the only thing in this case that can provide that force is, oh, bummer. Yeah, and that's where the conservation of energy, I don't like to use that term, but that's the reason that I have this soccer ball, big mass, big velocity. Like I said, if it's the only thing in the universe, you know what I mean, cool. If I introduce an air molecule to the universe, and then the soccer ball runs into it, And let's say this air molecule just attaches to the soccer ball, and now I have the soccer ball and the air molecule. Well, my mass grew, and then so therefore I'm going to have a change in velocity. The velocity is going to slow down. Why would it do that? Oh, that's interesting. That's fascinating. That's kind of the roadblock. It's like Oh, how is that related to force? Oh, yeah, because I got confused. When I said the air molecule just attached to the soccer ball, well, the air molecule is just chilling, 0 velocity. And the fact that the soccer ball's coming in with hella velocity, and then a little time later, you know what I mean? That air molecule is stuck to the soccer ball. So now the air molecule has the same velocity as the soccer ball. And if it did so, that mass of that air molecule changed velocity from 0 to the velocity of the soccer ball, and F equals ma. So we have that air molecule. It changed velocity, which is a change in velocity, change in time. That's acceleration. And that's a known quantity. We know what that velocity change was. I know the mass of that air molecule, and it required a force to do that. And in this case, the soccer ball is applying a force. It applied a force onto the air molecule during the time that this went from 0 to attaching. Yeah, so that's the other place where it's kind of gets confusing. And we have an equal and opposite reaction. That's fascinating. And I think you could almost treat it as this soccer ball is coming in with a spring. And then, so the soccer ball has a spring on the front of it, and here's the air molecule. And as the air molecule this spring gets tight, here's the soccer ball, here's the air molecule. This spring is now has a force on the soccer ball that way, and it has a force on the air molecule that way. And then let's say that happens, and then when the spring gets tight, you have a clip on the spring that clips it and locks it into place. And then the air molecule now rests inside the spring or something like that. And now the system is still moving that way. But because that time, there was a small change in time there during that impact, and the force on the spring was pushing the soccer ball that way, and the spring was pushing the air molecule that way. So that's what's happening in a collision. As long as you just treat the change in time as kind of small and treat it like a spring, that is a very good analogy, because that's what's happening. And it's kind of cool to have a massless spring be the connection, because that's what's happening. Like all molecules in a rigid structure, when they do impact, they are moving like springs. Like that's one way they move, is linearly, kind of like springs. They don't have to move linearly. Like all this can be a non-linear thing as well. The force doesn't have to be linear at all, and that's where the force could be any sort of equation. And then, that's where you use calculus to be like, hey, what's the average force? And so that average force happened during that change in time. And so F equals ma. And so if I know the force, and then I know the change in time, I can know the change in velocity because I know the mass is involved. Anyway, so that's real loose. We're not doing impacts, but I think it is useful to always kind of go over that in your head, just to make sure, like, hey, you kind of know what's going on. Anyway. Oh, man, I don't want to give up on this video. But, yeah, let's see. How could we do this? So we have... and then just in general, like I'm just going to say the things that are just more equation-y, is that what do I know about free-falling objects? Well, I know that if I drop this soccer ball off the cliff, it's like hardly moving, and then it's moving real fast, and then yeah, so its speed is linear, like but the distance that it's traveling is parabolic. So if I drop something, it's getting, you know, farther and farther away. It's the distance that it's traveling is not linear. The distance that it's traveling is just like, okay, it's chilling here, and then it's there, whoa, it's there, and oh, now it's way down there. You know what I mean? So that's kind of what happens. And so these are cool. It's cool to actually have some sort of velocity that way, horizontal, because that will be linear. That will go that way. That, you know, every change in time, it's going to go that particular distance. So then, one way to look at these is just like, well, actually, what does it actually look like? What's the shape of the curve? And so when I kick the soccer ball, it is going to be a parabola. That's the equation that we would get. But this is not the actual kinematic equation that we're probably going to be using. Maybe for this one for sure, because it's a red one. But this is height as a function of, you know, distance. So if I say this is my graph, where this is my x-axis, this is my y-axis, this is the radius r. So y is r, and then this is the radius r here. This is coordinate 0, 0. So this is the path that I would see the soccer ball go, and whoa, sorry about that. Let's say this is r, and this is the path that the soccer ball wants to go parabolically. But this is the shape of a half circle. You know what I mean? So I didn't draw it very good. Anyway, so that's the shape of a half circle. This is where the soccer ball wants to go. And so we actually need to have this parabolic shape, you know, like, yeah, that's fascinating. We need to give it some oomph. Let's actually draw a parabola. This will be actually really good. It's just really hard to draw. So I'm going to do two things. Well, one is a parabola from 0 to 1. So this is 1 and this is 1. And I'm going to have the equation y is equal to x squared. And so here's a point. It's going to be 1. And we're only going to be worried between 1 and 1. And so what do we do to this? If I throw in x is equal to 1/2, I'm going to do 1/2 times a half. That's going to be a quarter. So over here, I'm going to go to a quarter. And then I'm going to throw in x is equal to half. I'm going to just be right there. And then if I'm going to go to 1/4, this is just a 16th. So this is half, a quarter. I need to go an 1/8 and then a 16th. So this is my other point. So this is the shape of the parabola. You know, it's going to be something like that. Now, the shape of a half circle is, I don't think I drew this very good. Oh, yeah, no, I think we're good. Because the shape of a half circle, doesn't the circle go like this? And then come in like that. Yeah. So it even this kind of problem is interesting. It's just like, well, what are we talking about? How would we even be able to get this thing at all to not run into the block? That's kind of, from this visual, like that's kind of what this is showing me. Is just like, well, it seems real difficult for this to even not hit the block. Is that, like, where do these equations interact? I'm going to take my first break. All right, hell yeah. I'm glad I took that break, because what we're going to explore is just the y squared, like y is equal to x squared equation, parabolic equation. And so so here's our, let's draw this kind of crispy. All right, sweet. So this is coordinate 1, 1. And we had something where if we went half, it was just a quarter. And then so here's kind of our parabolic shape. And then even here we have a slope of 2, so that's substantial. But what's our slope of a circle? Our slope of a circle of this same is infinite. Like we have infinite slope there, and then we have a slope of 0. And then yeah, so that's kind of fascinating. So even just right here, the slope of a parabola is 0 right at the start, but then quickly becomes some sort of where the slope of a circle slowly changes, I think. But now, what do we know about this equation? If you've never played around with this x squared equation, what we can do is we could do 10x squared. No, that's not what we do. Well, let's play around with this, I guess. I don't think we actually want. I think we want to make this smaller, maybe. But let's say we make it big, and we're going to put in half. So 1/2 squared is going to be 1/4, and then we're going to have 1/4 of 10, which is 2. So if I go to half, yeah, I'm already. So yeah, so let's make this y is equal to let's say 1/2 x squared. So then if I throw in my value of 1/2, we're going to do 1/2 squared as 1/4, but then I'm even going to half that. So then this equation is going to go down by half. So everywhere where it's here, it's actually going to go reduced by half. Okay, so now we're getting somewhere. Because even if I drew this to scale, what I need this equation to do is to be like almost a third. You know what I mean? So let's say that. Let's say I got this y is equal to 1/3 x squared. You know, would we be money? Because I think it's going to hit right here. And if I'm already up here, I need this to be a third and just kind of down here. And then if this is, yeah, I don't know if I have this drawn to scale at all. But that helps. You know what I mean? So if I have this parameter, then that will definitely help out. All right, so, oh yeah, holy hell. So I always take things to the extreme. You know what I mean? So let's say my initial velocity is just huge. And so, like in 1 second, this thing's going to be here, and then it's going so fast that it's just going to take... Let's just say it takes 1/10 of a second to go from here to there. Like even just that. So if it takes just 1/10 of a second, and this is good because we get to play around with the gravity part. So if the change in time is 1/10 of a second, I don't want to write very much. What do we got? Yeah, and what would be the velocity? If we're saying this is 5 meters, and we travel 5 meters. So what is velocity? Velocity is change in position, change in time. And that's just average velocity. You know, I mean, if you're doing these big deltas, that's average velocity. But if velocity is constant, which it is in this case, it also is the actual velocity. So keep that in mind. And that's a little bit of the differentiation. I would have to make these very, very small. And as these get smaller, your change in x and change in t, you get a better approximation of the actual velocity at that point. But you're still getting the average between, you know, in that time frame between those two distances. Unless your velocity is constant. And that's kind of the calculus. Hell yeah, I think that was good. But yeah, change in position would be 5, and then change in time is 0.1. So 5 divided by 0.1 is 5 times 10 is 50. So this would be a velocity of 50 meters per second. And so what's going to happen due to gravity in 0.1 second? Well, in 1 second, we would change our speed from 0 to 10. And we've found out that that's a linear change in speed because gravity, this gravitation, is the acceleration of gravity is 10 meters per second. And so if we do have 1 second, we're going to change our velocity by 10. But if I'm going to multiply this by 0.1 seconds, hey, the seconds cancels, and I get a change in velocity of 1. Okay, and then so that's a change in velocity. So after this tenth of a second, I'm going to have 1 meter per second. I started at 0, so this thing's falling, and that's going to be an average velocity of 0.5 meters per second. And how far did I travel? Well, 0.5 meters per second. If I traveled 0.5 meters per second in 1 second, I'd travel 0.5 meters, but I did not travel that for 1 second. I only traveled for a tenth of a second. So it's just really good to go through those for these problems. Like, talk your way through that. Find your average velocity, and then what's the time frame on that? And so 0.5 meters per second, if I did it for a second, I'd go 0.5 meters, but I did it for a tenth of a second. So I'm going to go 0.05 meters. Cool. So I only go down. So in this case, I go over 5 meters and down 0.05 meters, which is 50 millimeters. That's 2 inches. So I go over 5 meters, about 15 feet, and I go down 2 inches. Hell yeah. Now for this, though, it's just like, you know what I mean? That seems like we cleared this part of the circle over here. But now, like, for me, you know what I mean? I'm not satisfied enough. It's just like, well, how do I know that I cleared this part of the circle? You know what I mean? So that is kind of interesting. And, yeah. So now let's figure out what the equation of a circle is. And one way to do this is just by guesstimation. Like, actually get a 5-meter string and put a point on a big sheet of paper or out on a sidewalk, and then draw your x coordinate. Like, this would be kind of a fun little experiment, but even just talking your way through, like, hey, is there any way to actually just do this by hand and not equations? You know what I mean? If you don't know the equations, if you're stranded on a desert island, you can probably do this and be like, okay, this is the x coordinate 5 right there, and this is the y coordinate 5. And so I'm just going to divvy this up. I'm going to go 1, 2, and I can't, oh man, I'm going to do this left-handed. And it's going to get real bad. Just because I have like this hurt wrist or something. Yeah, it's just a bummer. When you do these problems and you're using a pencil, I'm going to get, luckily this isn't, well, I don't know. We'll see what it is. I don't think it's carpal tunnel or anything. All right, hell yeah. And then what you're going to do is then you're going to figure out what points you hit up here, and then you're going to document those points. You know, and you could do that. And so, yeah. And what are we going to find? Well, and then let's do the equation, because I don't even know. I mean, I could do that, but then I know that this is going to be 5. And this is where you could do a unit triangle, but I don't know. It's kind of nice not to do a unit triangle. We got 5. And I'm going to have some sort of angle here. And what do we know? And all angles are just documenting this. You know what I mean? All a right triangle is someone, you know, did this on a sidewalk with a string and of a circle. Like, all a right triangle. So when you're doing right triangles, you know what I mean? Your hypotenuse is the radius of a circle. And this is just giving you your x and y coordinate. So if here's the angle and we say the sun is shining, this is the sine component. This is the cosine component. And so, and the sine component is a percentage. So just think about that. It's a percentage of the hypotenuse. And so sine and cosine are always going to be numbers between 0 and 1. You know, like 0.5 or 0.866. And so that's helpful. And cool. So then these are the actual coordinates as a function of this angle. And oh yeah, how would you do this from Oh yeah, so we could do that. We could, but yeah. So now my brain is fully racked, and yeah, this is where mathematics is kind of tricky, because I'm just gonna say this is just any generic x. I'm gonna say, hey, like this is an equation now. This is going to be an equation where we have y is something something x. That's kind of what I do, and it's going to be linear, where I can put y on one side and then the other thing. Well, even though you can have an equation, doesn't mean you can explain the equation with just normal mathematical things. You can get an equation that's just still linear. I think that's what you would call linear, but it's too difficult to graph with just like normal operations. But hell yeah, so we're going to have our x term here, and then this height is just going to be a generic y term. And because we have, and this is using Pythagorean's theorem. It's just like, what do we know about a right triangle? If I square this and add it to this squared, it's going to be 5 squared. So that's the equation. So we have x, and that's literally, how is that the equation of this? Well, we're going to rearrange it. So we have x squared plus y squared is equal to 5. And, I can't do, I'm going to try to do this left-handed, because, like, if my wrist is going to hurt, I need to even start writing left-handed. All right, how do we isolate y by itself? We're going to get this to the other side. Oh, and this is 5 squared. My bad. So it's the radius squared. So, hell yeah. So y is just going to be the radius squared minus x squared, and then the square root of that. Cool. Okay. So I'm definitely going to write that, because we're gonna need that. So the equation of a circle is y is equal to x squared. Sorry. Anytime that you're doing this square root of something squared plus the other thing squared or minus, if you're doing the minus part, this always has to be the hypotenuse. I don't think there's a scenario where this isn't the hypotenuse. Does that make sense? So you got, because you're always taking the bigger thing, subtracting one of the sides, and then with this squaring, and then you're going to get one of the other sides. And what do we know about a right triangle? Hypotenuse is always the biggest thing, and then the sides are components, sine and cosine components, or percentages of the hypotenuse. I mean, that's where I think middle school does a disservice, where you say like the fractional components, where you're just like, if this is your angle, and sine of this angle is going to be the opposite over the hypotenuse. Well, the hypotenuse is always going to be the bigger number, and something smaller divided by the hypotenuse is a relationship between these, and it's just a fraction. But I think fractions and proportions don't set in as well as this. That was the first thing that got me making videos, is just being like, hey, if you treat sine and cosine as a percentage of the hypotenuse, that'll change your world. Hell yeah. And then maybe go back and then think of it as a proportion. And what the hell is a proportion? Cool, it's a percentage. A proportion times 100% is just a percentage. You know what I mean? So hell yeah. As long as the bottom thing is the bigger number, and this component is related to that. And that's what we're saying. We're saying this side is related to this bigger side, based on sine of the angle. And those are just, they're not totally made up numbers, because, but they're very difficult, because you have to use like a series. Like I think the Taylor series is one that I've used. I don't know if that's the only one that you can use. No, it's like when it comes to doing series, I'm sure you can do multiple different ways to get the same thing. But yes, to get the actual, for sines and cosines, there's only a few that just kind of pop, like 1/2, but that's about it, I think. Yep, you got square root 2 divided by 2, square root 3 divided by 2, and stuff like that, square root 2 divided by 2. But besides that, everything else is hell, and just feels made up. All right, so, but yeah, so here's our equation. And so now, all I want to do is just throw in where we can overshoot this, like once. Where if, like, I throw in, Yeah. I throw in my, how are we gonna do this? I like keeping the radius at 5. I'm gonna do that. Change in time is yeah, let's do this. So I'm gonna do radius of 5. Change in time is 0.1 second, and my velocity of this thing is gonna be 10. And so yeah, so now my velocity of the soccer ball is 10. I don't know how I did it before. Maybe I did it wrong. But anyway, so and then in 1/10 of a second, I'm going to be at 1 meter. So if this thing is 5 meters, at 1/10 of a second, I'm going to be right there. But then I also dropped. And we found that if I'm dropping for 1/10 of a second under gravity, I'm going to have a velocity of 1, average velocity of 0.5. And I'm going to have that for 1/10. So I'm going to have 0.05 meters. That is going to be my y height. You know, it's going to be down 0.05. Now, we're I don't know how we're going to look at this, because well, no, yeah, this was the equation. This equation perfectly matches this right here. So hell yeah. So we do have it, and then so I'm going to say at 1, when I throw in x is equal to 1 over here, I'm going to have 25 minus 1 is 24. So I have the square root of 24. So we're going to break out the calculator. So we have need to do this. So we have second square root 24. Hell yeah. And then I have to do 5 minus this. I'm going to do 5 minus that answer. So this is the first thing we've actually done. So 0.10. So perfect. So even like right here, if my speed is 10 meters per second, if I kick it 10 meters per second, which is not too fast, right? After it goes a distance of 1 meter horizontally, it is going to fall due to gravity 0.05. But the circle is going to be what did we say? The circle is going to be drop away at 0.1. Cool. So now what I'm going to do is going to take the same example and change my change in time to 1/10 of a second. 100th of a second, my bad. So we're going to do 100th of a second. So now I'm only 0.1 meter, you know, and then under gravity, I have only fallen for 100th of a second. So 10 divided by 100, or 10 times 100th, is 0.1. So now my velocity after 100th of a second is 0.1 meters per second. My average velocity is 0.05. But here's the kicker, is that I went 0.05 average velocity meters per second. Now the question is, how far did I go? Well, if I traveled this speed for a second, I would go this distance. If I traveled this speed for 1/10 of a second, I would go this distance. You know what I mean? This distance in meters. And then if I traveled this for 100th of a second, this is the distance I would travel. Cool. So now we have this. All we're doing is just reducing this by, well, no, this actually reduced by, 2 extra zeros. Just by changing the change in time, just another, drop the change in time 1/10. The distance of free fall dropped by a factor of 100. It didn't just drop by 10. Cool. And then when we throw in 0.1, if we have 100th of a second and we're going 10, that's going to be 0.1. So if we throw in 0.1 meters here, break out our calculator. So we're going to have, let's try to just do this once. We're going to have 5 minus the square root of 5 squared minus, but you know what? I didn't know that this was the equation right off the bat, you know what I mean? So that, and I've done these before. So there's something in my knowledge that I haven't done these enough, but I think that happens all the time. So I just don't fret about that. I know that physics is from the fundamentals. I mean, and even though this isn't even physics, this is just math. I'm going to get some water. I still think that I'm doing a pretty good job. All right, pat myself on the back time. But yeah, you know what I mean, just what we're doing the fundamentals and showing the learning process. Like, I can't see this. You know, when I look at this problem, I'm not like, oh yeah, the equation of a circle. I never remember the equation of a circle. All right, so did I even type in the right thing? Isn't this just 0.1 meter? Because if we went for a hundredth of a second times 10 is 0.1. So this has got to be just 0.1. And we're going to square it. Oh, hell yeah. I can use my keyboard too. This is pretty sweet. And then what were we going to get? Hell yeah. And that just dropped by a factor of 100. So for sure. So there you go. So we even can we can see that it's not 10. So now this is the point in the game that is just like, well, let's do the same process for a different value. So I'm going to say 5 meters per second. So let's go back to here and see if we can do that. Oh, damn it. Did not want to do that, but we can do a little erase. All right, get those 4 and we're done. All right, so maybe those 2. OCD. All right, so what do we want to change our velocity to? How about for just 5 meters? You know what I mean? I think 5 meters per second if we have our velocity. I don't think so. I think it's not going to be good enough, but maybe. All right, and then so if we kick 5 meters a second, and we do a tenth of a second, so this thing is just going 0.5. You know what I mean? Can we agree on that? The thing went 0.5 meters. This equation, want to do this one first? Hell yeah. Is going to be, hell yeah. So now we have a distance of 0.5. Yeah, so that should work. And we get 0.025. Okay, so let's come back to here. Okay, and what up? So now we need to figure out what gravity is doing. So we're going to go tenth of a second. Our gravity is 10. So if we free fall for a tenth of a second, we're going to pick up 1 meter per second in velocity, average speed of 0.5. We're going to have an average speed of 0.5. If we traveled 0.5 meters per second for a second, we traveled 0.5 meters. But we traveled for a tenth of a second. So that is, I always do that verbiage every time because this time thing comes up twice. You know what I mean? And that kind of shows that it kind of comes up twice. So I didn't travel 0.5 meters per second for a second. I only traveled for a tenth. So we go 0.05. So 0.05, and then that's the distance that we traveled. This is 0.02. Yes, so those do collide. Under gravity, I traveled downward 0.5, and then the circle only went down by 0.025. Okay, hell yeah. And this is, I think, a very useful skill to just play the mountain climber. Price is Right was a game where it's just like, we chose 10, it was too much, chose 5, let's do 7. And even here, it's just like, you can get tricky if you want. You can do like, hey, let's try 7.5 and see if you nail it. So yeah, let's see if we can do a more complex number. So we're going to come here, and we're going to go, pull this up. We're going to go, I don't know what the keyboard shortcuts are, but we're going to go 7.5. Ah, bummer. What? Oh, whoa. We're going to go a velocity of 7.5 for a tenth of a second. So this is going to be 0.75. Okay, so now this is the distance that we'd be going. This is the distance of the circle. So if we do 7.5 meters, what are we talking about? We're going to have a velocity of 7.5, a time of 0.1 second. If we free fall in this direction, and then we need, did I mess this up? No, I don't think I did. Because if I have a velocity this way of 7.5 and our time frame is 0.1 second, my distance this way is 0.75. And that's what we did on this calculator, 0.75. Hell yeah. Yeah, we're almost done with this one. I mean, we're done with this one from just kind of like the guess and check to get the answer. But I think that is more crucial. I'm probably going to leave this one at this because I don't want to approach the 3-hour mark. But we did pretty good. I mean, then you can go and be like, well, no, I'm actually going to use the equation of, you know what I mean? And I don't know why they didn't teach physics as a differential equation, because acceleration is x dot dot, you know what I mean? MIT would do that. Acceleration is d squared x and then dt squared, which this is in parentheses. The d gets the second derivative, and this is just second derivative of x, where you would have the first derivative of velocity, you know what I mean, with respect to time. And then velocity is just derivative of position with respect to time. So that's literally what you're putting in those into that parentheses. And so this is how you can write it. And I think this, and then this too, like you should almost write this as dd. You know, I've never done that before. But look at this, d times d, the you know what I mean, if you're calling this, you know, a property or whatever. But hell yeah. And then you'll have x, and then dt, you're going to have two of them downstairs, and for sure it's going to be dt times dt. But you're going to have this d times d, and what the hell is d? You know what I mean? I think it gets kind of confusing from that perspective anyway. Just because, like, hey, right here, I can pick this up. I think this is a change in position, change in time, and then this is a change in the change, you know, a change in this parameter, which then it's kind of easy just to call this velocity, and I can say a change in the velocity, a differential change, a very small change and a very small change in time. But that's where all the pros for sure use delta, you know what I mean? I think even from the YouTube geniuses, because then you can bring up the limits. This is a quantifiable change, so we have change in x, change in time, and then if I want to get to the differential, I'm going to say change in time approaches 0, and so then I use this word limit. You know, maybe if they just got rid of the word limit, people would be okay with calculus. You know what I mean? Just you can never say the word limit like that. That would be useful because I've never said it. Hell yeah, just say change in time goes to 0, and then we kind of know what you're talking about. Booyah. I think the second you say limit, you scare people away. Hell yeah, sounds like a cheap soda. Where are we at? Yeah, we're getting pretty close. All right, let's back this up. Oh, no way. I can only back up so far. Anyway, we need to keep that on the screen. So we did this. So we got that, and now we're going to figure out the gravity. So 0.1 second, I'm going to pick up 1 meter of speed. And this one doesn't change, actually. This one has nothing to do with the 7.5 at all. We've already done this one. It's just 1 meter per second. is our speed after a tenth of a second. Average speed is 0.5. And we traveled that for a tenth of a second. So our distance is 0.05, and this is what we fell. And that's the distance this way. So hopefully the circle is more than 0.05. And see, now this problem is ringing a bell. And it is. It's 0.056. Hell yeah. So now, like, you know what I mean? You could still do this process back and forth. Oh, I hope these jokes don't pop up. If they do, yeah, I'm a joke writer, and so, I don't know, you probably just write horrible sex stuff. I don't think there's anything racist, but you always start with just the most horrible, you know, unimaginable, and then you try to, like, oh, and then let's just make a word joke. Like, anyway, yeah, sorry about that. But, yeah, if that pops up, take a screenshot, and then frame me. It's just the life of a comedian writer. You don't want to share your work in progress. And it's not that you're a bad person. It's just like you're just, oh yeah, let's just use the worst of the worst, and then you know what I mean, make some quality jokes. Yeah, we're almost done with this one, and we got an answer. 7.5 sounds legit. He better kick at 7.5. And what are you gonna tell this person? You know what I mean? What is this, soccer person? You gonna tell this person you're gonna have to kick 7.45? Hell no. Hell no. And then what we got here is like this thing don't change. Oh yeah, that's fascinating. And are we taking this thing down enough? Yeah, what if this position, what if we do a hundredth of a second on this one? So yeah, let's do that. So if we did 100th of a second, this thing is going to go to 0.075 squared. And we're going to get 5.6. We're basically going to get the same number. And aren't we going to get the same number here? Yeah, we've already done that. That's kind of fascinating that we're going to get the same number here. And so, and I don't understand that. I think it feels like something's wrong on that perspective, but maybe it's not. Oh, you know why it's not wrong? Or here's my thought on that. It's that because yeah, I remember this problem. Because this is like an x squared, if it is too low, and then here's your radius, Oh, you know what? Now, we've been bumming this one up because we're only checking, like, right off the bat. And, but no, it's interesting. Like, I think, no, we already talked about that. We said that if the parabola is too low, it's going to do that. And then we have to get to the point where it actually doesn't hit. And I was just assuming that it that has to, like, when we get very close to the velocity, that this actually will shoot off the edge. That is going to happen, like, the place that it's going to be most risky to hit this hemisphere is going to be really close. It's not going to come down here and clip right there. So that's what I was assuming. But we could double check that. And this is where, you know what I mean? How do we double check that? I know that at halfway, that's a risky place. And then, or just when x is square root 2 divided by 2. So 0.707. So I could put 0.707 here. So let's do that. So we're going to pop up here, and I'm going to go 0.707. Cool. And we get that value, 0.05. And does that make sense? No. No, I apologize. No, that has to be 0.707 times 5. You know what I mean? It's 70% of 5. So I'm going to come in here and do times 5. We need some parentheses. Oops. Oh, I did I got to hit second. 0.707. All right, so now do we have it? 0.707 times 5. So that's our x position. All right, I'm looking good on that. And so we have a 1.46. So that's the distance down at the halfway point. Hopefully I did that right. Does that look about right? Halfway, yeah, it looks like you only drop, you know what I mean, not very much, point, you know what I mean, whatever it was. Cool. Okay, so now let's figure out if we're using this 7. We thought this was pretty close. Let's do the gravity. So if we are a distance out here of 0.707, how long did that take to get out to that distance? We have this velocity, 7.5 meters per second. Sometimes I use the units are the equation. And this is a distance in meters. And I want to know time. Time is downstairs on this one. I need it upstairs. And so I need to take this number and divide it by that. And then meters will cancel. Seconds will pop upstairs. That's how I'm going to do that. So we have 0.707 divided by 7.5. And that's not even right. We have to take this 5 times 0.707. That's the distance out halfway. Is, hell yeah. Cool. So let's pop to our calculator. We're going to go 5 times 0.707. And then we're going to divide it by 7.5. That looks good. So what did we even do? This is going to be the time. So now we have a time of 0.47. We're going to multiply by 10. That's going to be our velocity. We're going to divide by 2. That's going to be our average velocity. Excuse me. And that's going to be our average velocity for this time. So we're going to, this is our meters per second, and then we're going to multiply it by this time. And so that's our distance, 1.11. So we drop a distance of 1.11, and the circle is down 1.46. And so those two numbers are diverging. And so I'm going to say, cool, we're pretty much good on that. I'm going to erase this all. And yeah, so now we're basically about there. So we have y is equal to square root 5 squared minus x squared. And now we're just going to try to chisel this out and see if we can get just a little bit crispier. And this is where I kind of just use the calculator. So I'm going to what am I going to pull up? I'm going to pull up this one and change the velocity. I'm going to change the distance to 0.76. I'm going to go 0.74. I think that's going to get closer. Cool. And then, well, no. Let's go 0.7. All right, so now we have a speed of 7 meters per second, and this is our distance. And that's 1/10 of a second. but wasn't our time for 1 second 0.5? Our time was 0.4. So yeah, so now we know for if we're just using 1/10 of a second as our fall, if we're running our horizontal velocity for a second, then we're falling for a second. That means, and I'm sorry, 1/10 of a second. If we're running our horizontal velocity for 1/10 of a second, that's where this 7 becomes 0.7. Our free fall is going to be for 1/10 of a second. But at a change in velocity of 10 meters per second, that's going to be a change in velocity of 1. I'm going to go from 0 to 1. My average speed is 0.5. Now, I didn't travel 0.5 meters per second, that average speed, for a full second. Just 1/10 of a second, so we get 0.05. So this answer is wrong. And so now I should just be able to hone in on this and then just chisel this out until we get something that's 0.5. Now, I could be wrong on this, but 0.71, I think, yeah. So, and maybe it is 0.7, let's throw in 0.707. 0.7071. Well, let me try that, because that'd be kind of cool if it was approaching square root 2 divided by 2. Whoa, did not do that right. Oh, bummer. Let's pull this up. Let's do square root 2 divided by 2. Insert some parentheses. I need the keyboard shortcut for insert because I use that all the time. But I do like this. Hell yeah. Nah, I mean, but 0.707, 0.71, probably the answer in the back of the book. So now let's do it. You know what I mean? And that's going to conclude our video. You know what I mean? We did this from basics, and then I mean, there was some math involved in being like, oh, I need to know the equation of a circle, but we slow rolled that too. And cool. So this is problem 54. This is, what chapter is this? Chapter 4. So problem 54 in chapter 4. Let's go to the end. Go to the solutions. Chapter 4. All right, so we should be right here. Chapter 4, problem 54. Oh, it's not even in here. Oh, that's a bummer. But I think we did it. See, that is the juicy way to do problems, where it's just like, do you think we could better life on that? Yeah, I think so. Should we go back and see if we can, take one more look at it? Just from equations perspective, maybe? Yeah, I think so. So this is chapter 4. These are the problems for chapter 4. And we got 54. I think we can do it. Yeah, but this is probably the place where it's going to get slow. I don't think it is. So we have acceleration is dv dt, and so this is a differential equation, and it's equal to 10. I'm just going to use 10, and we can change it to 9.8 later. Cool. And we're going to separate variables and then integrate, and you're going to get velocity is 10t. It's plus a constant, but what we're going to say is that, and this is just the y direction. That's the one we were kind of interested in because we're going to go that way, right? And then what do we got? And then so the second week at time 0, our y velocity is 0. So if this was a constant, this would be 0, and we're good to go. And now we're going to say this is change in x, change in t, which is a differential equation. And what I'm getting better at is, like, this is the differential equation. It's equal to this. Now, this isn't and then we talk about solutions. Just as this was a differential equation, and then when we integrated, we came up with a c. So it just says change in velocity and change in time was 10. Like if I take this over here and then I'm plotting on a graph change in velocity and then change in time, I'm going to have a constant. You know what I mean? And in this, I'm sure they've done this, but this is the first time I've ever I don't even know if that you could do this. You know what I mean? That's the crazy thing about calculus. It's like, what can I do? What can I not do? And then yeah, so that's gonna be 10. Well, yeah. But I guess the question is, because this is change in velocity, cool. I want to know I want to know velocity as a function of time. And that is going to be like that. And it's going to have a slope of 10 because this is the slope of this, you know what I mean, of this thing. And this equation can be anywhere in this, in this. Depending if we drop it off a cliff, it has 0 velocity and then picked up some velocity. Maybe we started it with we threw it off the cliff and it started, we threw it off the cliff that way and then it picked up some velocity. All right. So, cool. And then we separate variables again and then integrate and we get position and we integrate with respect to t, so this becomes t squared divided by 2, and so we get 5t squared. But we still have a constant, and for this problem, now we need to be very careful, because when I do this y is equal to, I'm going to say y is equal to the square root of 25 minus x squared. Or this is just r. Cool. That's going to say when x is equal to 0, I'm going to be up here. So that is this function right there. So that's the equation for that function. So I need my position, and this, when the person kicks it, that's going to be time 0. So time 0 is up there, and that position is way the hell up there. So when I get my position equation, when I integrate this, it's going to be, and I already wrote it, but let's write it over here. It's going to be 5t squared, but we have plus a constant. And I can insert something there, and I can insert something there. I mean, this is the equation, so I'm going to insert time is equal to 0. This is going to be 0, but my position has to be r. You know, I know that. You know what I mean? And then so c has to be r. Hell yeah. So this is my equation. And, but this is a position as a function of time. I need this to look like y. I need this to look like height, my height y. Oh, whoa. And then my bad. This has to be y. This is the y direction anyway. So this, and this is where I get bummed up on these kinematic ones. I just assume it's the x direction. But this is velocity in the y direction, so this is not dx dt, it's dy dt. And there's no difference in y and x, it's just two different directions. They're the same parameters, one is just a velocity. When we drop stuff, we have usually velocity in that direction. And that's going to be y. So we have y is equal to, so this is y is equal to 5t squared plus r. But this is not y is equal to x. I need y as a function of x. And I don't even know how to do that. You know what I mean? And, but no, we do. But, and it's just fascinating. So we did this whole differential process for the y direction. We're going to do it again for the x direction. So that's kind of kinematics in a nutshell. You have to do it for both directions. You're going to get two equations as a function of time. But, you know what I mean? And you're going to get an x as a function of t, but that's still not x. You're still not going to get x as a function, you know, something y. You know what I mean? You're going to get x as something t. But now you have two equations. You have x and y, and they're the same time. You know what I mean? At time is equal to 0, this is where the x is, and this is where the y is. So those are the relationships that you're going to have. And so let's do this. You're going to have acceleration in the x direction. There is none. And again, from the basics, there is no Earth over here. So every time I say there, you know what I mean? Hey, if you got something moving in this direction, there is no Earth over here pulling it that way. Now, there might be other known forces. You know what I mean? Other things can provide force. Moving molecules, like wind, can provide a force. It can change that velocity, you know, in both directions. It could speed this soccer ball up or slow it down. So just remember that. And why can mass change velocity? It's not just because it's mass. It's because it's running into mass, and that mass is moving. And the only way to do that is to apply a force on that mass. So whether you're the soccer ball hitting that air molecule, you are providing the force on that mass. But then we have this idea that if you only have a soccer ball and an air molecule in the universe, if one applies a force on the other applies the force on the one. And so that's where we go back to, you can think of there's a spring between here. When they do impact, that spring is squishing. And even if it just locks into place and this air molecule gets into a cradle, during that spring crunching, we did apply a force in that direction and a force in that direction. So you can think of the spring as like attached to the soccer ball, but also at the same time not. You know what I mean? It's just that the second these particles collide, you just invented and poofed into reality a massless spring. And as that spring is changing shape and squishing, it's applying an equal force that way and equal force that way. So I'm glad I talked about that. And more water, and we're almost done. But I would do a problem like this. I would probably do every single problem in the universe like this. Start with fundamentals, play around with numbers, like forget remembering the equation of a circle, even though like that's really useful, you know, in XY coordinates and polar coordinates. But I just know that you're not going to remember those. Like if you neglect your studies for, even if you're in college and stuff, and you know, take a summer off, you're just in it. It's like no one's teaching you the basics on a daily. You're just expected to know it, and if you don't, then it's just, I don't know how you're going to refresh and increase your basics. And hell yeah. All right, so let's get to it. This is dv dt, separate variables, we get v. And then we don't have any t, so it just becomes a constant. And so our velocity in the x direction is this constant, has to be. So that has to be vi. And then moving on, this is going to be dx dt. And then separate variables, and we get x. And now we're going to integrate this with respect to t. There is no t, but we have a constant, so we're going to get vit. So this is the position as a function of time, and that makes sense as we've been using the entire time. We've been saying like, hey, this speed is 7, and I went from 0.1 seconds. Cool, I traveled 0.7 meters. We've been using this all day, and I think that is the clicker. Is where you're just like, oh, I was putting these numbers into my calculator like all day, and now I can see that this is the equation that I was using, and I think that sticks. Hell yeah. But this is still not x as a function of something something y. You know what I mean? Where I could switch it and then find y as I want to know what that parabola actually looks like. And I think that these problems are cool because when you're doing kinematics, it's easy to get this y as a function of t and x as a function of t. And then maybe, you know, the time it takes for it to collide with the ground, because well, I don't know why. Well, because you could throw in y is equal to 0, and you could find that time, and then you could throw in the time over here, and you could find the x. And we're going to have to do that anyway. You know what I mean? So that's the second part of that problem. But this is the trickiest. Is just like, well, I need to solve this for t or this for t. You could do it either way and sub one into the other. Like this is just a parabolic equation. I mean, is that what you call it? Parabolic. What is that? What is that equation that you use? Is that the parabola? You know what I mean? 4ac squared minus 5. b negative b squared plus or minus. And then, anyway, so you could solve this for t. That'd be kind of a cool thing to do, to be like, hell yeah, easy to solve this for t and then shove it into here. But you could solve this for t. You're going to have a one solution. You're going to have two solutions. One's probably going to be normal, and then one's not going to make sense. But anyway, let's do this. So we're going to solve this for, let's get the hell this out of here. Yeah, we can do whatever we want now. We've kind of passed the 2-hour mark. I can feel it. We're going on the 3 plus. That's all right. 3 hours, one problem. All right, so if I solve for t, that's just going to be x divided by vi. All right, now we're money. And then so I'm going to have t right here, and I'm going to square it. So I'm going to have x squared divided by vi squared. That's what I'm going to put in here. I'm going to multiply by 5. All right, so, and then I'm going to add it to r. And then, so here's the equation. And this is equal to y. So finally, I have a y is equal to equation. All right, now, for the life of me, I don't know how to, this is the y is equal to our equation. And what we want to do is solve it for velocity. And so what I want to make is I want to have the y's equal. I want to know, like, hey, the y's can hit, but I want to know the velocity that makes them just touch, maybe. Yeah, I think this problem only works as if this doesn't hit twice. That was the weird thing about this. It's just like, well, how do I know this parabola doesn't clear it and then come back down and knock into it? It's because just the way this problem is natured, that if it can't clear it over here, it is actually running into it right off the start. And then the second it does clear it, it will clear it. And so I think that is what's happening mathematically. Don't quote me on that. But if we put these equal to each other, actually I don't know. Like, what are we actually trying to do now? We have this as a function. Like, this is what we'd actually be looking at. Oh yeah, so this is the function of this equation. And we let's rewrite these. So this is 5x squared divided by vi squared plus r. And I just want to make sure this is true for our x equation, and this is half the acceleration t squared plus the initial height. So we're good there. We don't have any initial velocity on that y. So from this kinematic equation, we're good. And let's see what we got. Yeah, and so when we get this downstairs and we plug it in here, that's going to be x squared divided by vi squared. And we're going to multiply by 5, add r. All right, sweet. So I'm going to write all three of those equations. So we have x is equal to, I don't want to do the vi, but whatever. V squared, we have y is equal to 5 t squared plus r. And then we have equation of a circle, y is equal to the square root of 5 squared minus x squared. And then we have, when we sub these together, we're going to get y is equal to 5x squared divided by v squared. And, yeah, let's just do that. Whoops. V squared plus r. Okay, and so let's see. Yeah, and so I'm relating these two. Now, like like this I can just graph. I know what that looks like. The shape of this hemisphere does not change, but this is the parameter that can actually change. And what I want to know is if those two equations overlap. And what do we know about when equations overlap? We know that point, the x value of equation 1 and the y value of equation 1 is the same as the x value of equation 2 and the y value of equation 2. Damn it, I need more ice water. It's the last of the ice water. I don't know if I can finish, but we'll see. Yeah, so either the x's are equal or the y's are equal. So I can do either one. And since we have the y's are equal, and then so that's going to be, yeah, so and that's going to be the velocity. So I know that if I solve for velocity, that is the point where it actually touches. And then I'm going to get that, and then I don't trust it, you know what I mean? Because maybe it touches twice. But yeah, let's put them together and see. Okay, so this is equal to that, and I want to solve for this. So I'm basically going to get the v squared upstairs, and then all of this downstairs. So I'm going to have all of this downstairs. When I put this over here, I'm going to get it downstairs. This goes upstairs, v squared. And then I'm going to square root the entire thing. So this becomes the square root of 5x. So I have the square root of 5x. But this gets, you know, Haggerish. This is the fourth root of all that. 5 squared minus x squared. Is this what we really even want to do? Oh, what am I even doing? No. Yeah. Oh, yep. Maybe that's why this is a red problem, because yeah, it's going to be like a fourth root. Is that why it's red? Where you're just like, ah, darn it, I don't know what mathematical operations to even use. But if I got this over here, I would just square both sides. So I'm going to have 5 squared minus x squared is equal to, and this would be 5 squared x to the fourth. That's what I would have upstairs. And then I would have divided by v to the fourth. So then I would get these, yeah, so then I would just get these multiplied by v to the fourth. How would I do that? Oh, is this really what I want? This is so fascinating. Yeah, this is where I would take a pause. I have these two equations, and obviously I can, and this is where I could just do it guess and check. You know what I mean? Where I just like, it's the same thing, where when I put in this equation into the calculator, and this is the fascinating thing. Like if I put this equation into the calculator, it's the actual, what that circle looks like, that hemisphere from the side view. And then if I put this in and choose a speed of 7.5, it is going to be an equation. And so let's just at least do that, so we're doing something. This is, and we already messed this equation. This is just y is equal to 5x squared, 5 times x squared v squared. So let's go to our calculator. All right, so that's good enough. And we're going to graph some stuff. We got 5x squared divided by 7.07 squared. Cool. And then the next graph is going to be the square root of 25 minus x squared. Hell yeah. All right, let's graph that and see. And this is going to be, it's going to be 5 to 5. Yeah, so just zoom standard, whatever. All right, hell yeah. Oh, bummer. So this, yeah, why is that upside down? Oh, well, I'm glad I graphed that, because this parabola, oh, that's oh, I hate kinematics for this, just because negatives can bust your day. So we have, so our equation of gravity is going to be a negative 10. You know what I mean? So we have a negative 10. And so our equation is a negative 5x squared. You know what I mean? So that part. You know, this was going to be, the horizontal speed is in the positive x direction, but we set our coordinates where this is positive x and this is positive y. So yes. So yep. Those trip you up, because you're just like, man, we just spent all this time and it was just a negative thing, and it's just like, bummer. Anyway, so we're going to insert a negative. Hell yeah. Graph it up. Oh. Yeah. Oh, man. And, oh, but that wasn't even the equation. So we need to go back to the actual equation. So this, oh, oh, see, I missed this R term. 100%. Oh, there it is. So this is messing me up. So this is from before. This is our equation. So we need a negative here, but then we have a plus R. So hell yeah. So I think now we should be good to go. Oh, whoa. Don't want to do that. Okay, so. And then so we have a plus 5. All right, graph it up. Hell yeah. And then we're going to zoom in. We're going to do a little zoom box. Yeah, and hopefully we can see this. You know what I mean? Hell yeah. Let's bust this up. Get it bigger. Yeah, and I think, you know what I mean? And then we're just going to trace it out. And so that's kind of cool, because we chose just a value. We chose 7. You know what I mean? Nothing too crazy. This is the circle. Red is the circle. Blue is this. Blue should always be bigger. So what we're looking at is the y value. This blue should be bigger. And they're the same. And blue should be bigger. And it is. See how blue is 101 and red is 107. So hell yeah. So having a solution of 0.707, you know, was a good enough solution. It's not the exact solution, but hell yeah. So we're at least good there. And what we're, oh yeah, this is where my knowledge is just like, I'm trying to find the intersection of two lines. I really want to pause the video to get ice water, but which we will. All right, catch you on the flip side. All right, hell yeah. So last round, and this is kind of interesting. Well, I'm just going to say a couple words that doing problems like we've been doing them, you know, from an intuitive perspective, keeps the reality. You know what I mean? It's just like, oh, I know what's going on. I know why it's falling, what the time frame is. I mean, it's got horizontal velocity. I can kind of do some easy calculations to figure that out. That's how we got this relation. But now we're down to the nitty gritty that we have two equations, you know what I mean, that are and so now we're getting back into the problem. So I'm used to finding, you know, the solution, you know, solving for x. And when we have that, it's always where x crosses 0. And that's because we have, and I've never really understood that, because we have like y is equal to x squared. And I want to know, you know what I mean? Well, and then when I set this equal to 0, that is when, so x is going to be 0. So if x is 0, that's going to be a solution to when y is 0. And so why is that useful? I have no idea. Why would I want to know that? And why is that even a solution? If I have an equation where it's y is equal to x squared, and then I set y is equal to 0, cool. It solves for that. I mean, you could have x squared plus 2, and then that's your y is equals, and I'm going to set y is equal to 0. And, yeah, and that's where, when I have a y value of 0, the x value is going to be on the equation. Oh, yeah, so this is an equation of a line. So I have x squared plus 2, and that has no solution. So let's change this to minus. So I have x squared minus 2. And what I have is when I throw in a value of y equals 0, I want to know if that equation goes through, has a solution. Is that what you say? Where if I throw this value of y is equal to 0, is there a value of x where that has an actual value that makes this equation 0? And that it does for this one. And I could say x squared minus 1. That's going to be easier. X squared minus 1, because I could have x is 1. And that's going to be right there. X is 1. 1 squared is 1. 1 minus 1 is 0. So that solves for that. So that's where we have an equation, x squared minus 1. I'm setting the y equal to 0. And yeah, my brain is just like, why do you even want to do that? I have no idea. It's so fascinating. Math is weird because there's no I don't, the second I actually use a problem where this pops up and be like, hell yeah, that makes sense. But now what we have is two equations where we have, and our equations are this, the equation of a circle y, and then we have the other equation, and it's kind of covered by this calculator. So we're going to get this over here. Whoops. Yeah, because we still probably want that calculator at some point. All right, but this is our equation of the soccer ball. And what I'm interested in is just a point where those two equations meet. So if I have like this, and then you can think of it this way, or I'm going to think of it this way. This is my xy. This equation is y is equal to 0. Okay, and then this is my equation, x squared minus 1. Cool. And then I want to know where these two equations are equal to 0. So this is y is equal to x squared. This is y is equal to 0. I know that this, and that's where we get these are two functions. So now you can see that this is an equation of a line at y is equal to 0. That makes more sense now. And when these two equations cross, this y value is equal to that y value. This x value that doesn't appear in this equation is equal to this x value. And so, so if I set the y's, and then perfect. So then if I set this y is equal to 0. So I'm going to shove that into this. So I have two equations, two unknowns. So I have the relationship between these two functions. And when I put this 0 up into here, then if there is a value of this x that satisfies this equation, I have my answer. So even right now, I can actually do this in my calculator, because I don't think, because my brother said, he brought up the word like closed form solution. He's like, for some of these harder problems, there might not be a closed form solution where you can actually use operations of adding, subtracting, using all the parameters just in one go. Just like one, I can say like, hey, this is the answer and it's equal to the inputs of all the other things that we know. And so, yeah, maybe no closed form solution. But because when I plug this into here, I can graph this equation as just x squared Well, we have this value that we're trying to solve for, and I need to take another break. All right, hell yeah. So I think I'm almost there even mentally, because we're gonna put these two equations together, and we're gonna get what we saw in that TI-80, this calculator. And yeah, let's definitely get this in. Oh, I just do this. I'm gonna click on this, Windows up, Windows over. Cool, and we're gonna get those two. And the only place that we actually want them to touch is right at the top. And that makes sense to me now. We have two equations. They have to touch at the top, right? Because that's where they both start. That's where the sphere starts, and that's where the ball starts. But we can't have them touch any other location. So the only solution to these two has to be x is equal to 0. It can't have another solution. So I think that's going to be useful. And so here's our, and let me, I just, whoa. So this is negative 5x squared divided by v squared plus 5, and then we have the equation of a circle. So we're good there. So this is negative 5x squared plus r divided, and then this is negative 5x squared divided by v squared, and then plus r. This is my y, this is my y. So now we can put them together. Oh yeah, and oh, this is interesting. It's tripping me out, man. Oh, let's not put the y's. Let's see. I'm trying to put the y's together, and it seems like maybe I should put the x's. Both are gonna be awful, right? And then, oh, that's so fascinating because I have this third parameter that I don't know. Yeah, that's tripping me out. It really is. So is this one of those problems where you're just like, hey, you put these two equations together, and then you say that the x is 0, and then you figure out what that is? I mean, we could try that. So if I put these two equations together, and the x is 0, this part over here just becomes 5. So I have 5 is equal to, but if this is 0, then I don't even have a velocity no more. And so, oh, that is bizarre. Yeah. Oh, this is fascinating. I mean, I'm so glad I did this problem just from kind of the guess and check, because we kind of got our answer, and now we're just trying to figure out what are they, like the math. What are we trying to do? Yeah, I'm just gonna take a little break. Actually, I got to think about this. This is like one of those places. I like my style because it's just like everything. It can flow from one place to another, but man, it's like I'm kind of stumped because I have these two equations. I would put them together, and I would solve for the x value that makes them intersect. All right, let's put them together though. We are going to let's put them together. Huh. Oh, yeah. So if I put these two together and then subtract r over here, so I'm going to subtract r to the other side, and then maybe get v squared upstairs. So I could get v squared upstairs, 5x. Yeah, then I would have velocity as a function of x. Maybe that would work. So I'm going to have So I would have this. So sometimes I just like to be like, hey, this is that. Got it. And then I'm going to subtract r. Hell yeah. And then I'm going to switch places with those. So that's now downstairs. V squared is upstairs. Whoops, v squared. I always do that wrong. V squared is upstairs. And then I have 5x. So this is my equation. I have v squared is equal to 5x squared divided by 5 squared minus x. And hell yeah. So if this is a y is equal to x equation, maybe I do just want to graph this and see. All right, we're going to try that. So this is 5x squared divided by the equation of a circle minus r. So we got 5x squared. Whoop, didn't like that. All right, 5x squared divided by, parentheses, square root of 25 minus x. Nope, doesn't like, didn't like that. Holy hell. Whatever I hit, don't want to hit that again. So we have 5, doesn't like that x on my keyboard. 5x squared divided by, parentheses, square root 25 minus x squared. So I just did a backspace. Oh, that's what I'm hitting. Backspace. I need to hit the arrow keys, but we messed it up anyway. So we got 5x squared. And then we got to divide by the square root of 25 minus x squared. Hell yeah. And then minus r. Minus. And in this case, r is 5. And then we'll have to back that out. So that's kind of interesting. Yeah, I feel like I'm missing out on something, but whatever. Yeah, let's graph it. Oh, that equation's nowhere to be found. 5x squared? So what? 5x squared. So if x is 0, is 0. If x is 1, I would just have 5 divided by... Yeah, that should work. Yeah, why isn't that not graphing? 5x squared divided by the square root 25 minus x squared minus 5. Huh. Zoom out. change the window. We're going to do negative 100. Oh. Oh, I didn't like that. Negative 30. Wait, why isn't it X min, X max? I don't know. Oh, so there's that equation. Oh, it's way down there. Oh, but this should be negative. Yeah. Whoops, I totally forgot about that. I knew we were missing something small. Alright, so hell yeah. That's that negative. And we can probably clear our screen. Holy Toledo. Alright, now let's graph that. Whoop. Huh. All right. So now we're at a loss. That's so interesting that we just kind of chose values and it works, but we have no idea how to do the math to line these two up. And if I put these two equations to equal to each other, it would just be, let's see if we're just messing it up, because it would just be one of these minus the other. Yeah, so I'm sure we're messing something up. So let's clear this out, and we're going to do this equation. So I'm gonna try to, do you think I can copy? I don't think you can copy, bummer. Anyway, so we got negative, whoop. We got negative 5 x squared divided by 7.07 squared plus 5. Oh, yeah. Because we're putting them equal to each other, but we're trying to have this as a parameter that we're trying to solve for. Oh, this is wicked. Alright, so I think I'm just going to take a break on this. Alright, hell yeah. Okay, so this, I think I found my solution that I'm going to use. And so this is, I kind of did it on paper. This is what I wrote on, I didn't write very much. I just wrote that here's the equation of our circle. and we can just use all variables. So we have r squared minus x squared. Oh, and that was the interesting thing. I was using 5s and whatever here, but yeah. And then our equation of our projectile is going to be negative 5. Oh, come on. X squared divided by v squared. So I'm just going to say v squared plus r. Now we're going to set these equal to each other, and then I was just like, well, how do we compare these? And I was just like, well, and what we want is that this always has to be a smaller quantity. That's if I input any x, this all has to always be smaller than this one. So this is what I did. I was just like, well, let's square this one, and we get r squared minus x squared. And then let's square this one. And so when squaring, you're going to do it, FOIL method. You're going to have this squared, and then these two multiplied by each other, multiplied by 2. So that's kind of the general gist. And this 5 is not the radius that we were using. This is the gravity. This gravity. Okay, so I'm going to have negative 25. No, it's going to be positive 25. So we're going to have 25 x to the fourth divided by v to the fourth. Cool. Then I'm going to have plus r squared. And then I'm going to have minus. So we have a minus. And then we're going to have twice this. So I'm going to have 10 x squared r divided by v squared. And this is what I was comparing. And because I don't know if there's a mathematical way to be like, hey, this equation always has to be bigger, and then let's solve for this value that makes this equation always bigger. I have no idea. But this was my method, is that I saw both of these. So that these both represent y squared of the circle and then y squared of the projectile. And we're still saying that this has to be smaller and this has to be a taller number, bigger. So they both have r squareds, so I'm just going to get rid of that. So we don't have to compare that. But now what we're saying is that, hey, this number, when we compare this, so this has a value of negative 1. This has a value of negative 10rv squared. Cool. And if we compare those, and so now what we're going to compare is when x is really, so I don't know, this might only work if x is really small. Because if x is really small, this goes to 0. You know what I mean? It's very small anyway. And this drives. And what we have to say is that this has to be smaller. And so we're already multiplying by 10 and then some sort of radius. I guess the radius could be 0.01, you know what I mean? And so this could be a 0.1 upstairs. So that's where the v would have to be a smaller number downstairs, to make up. But yeah, we have this relationship that, and then instead of saying that this has to be less than, let's just make them equal. You know what I mean? So then this negative 1 has to equal this. So I'm going to have negative 1 has to equal negative 10 r v squared. And it might just be for the case where it's just x is really small, you know what I mean, kind of like right in this window. But yeah, I just found that we're going to get an answer that's going to be satisfying to me, and it's going to be that 0.707. Heck yeah, square root 2 divided by 2. So the negatives cancel. We're going to get the v squared upstairs, and then we're going to take the square root. So v is equal to the square root of 10r. And for our problem, this worked out, especially when we were using really small x, because this part of the equation wouldn't drive this would drive, and we have to get a v that's compatible where the y's are very close, but where this one is always just slightly bigger. And so for this to be slightly bigger, oh, that's interesting, where, oh, but these are negatives. These are negatives. So when v is, so if they are equal, and for our problem, it was square root 10, and then the radius was 5. So that's this square root of 50. And the square root of 50 is 0.707. I don't know why that is. Square root 50, you can do it in my own calculator. It's 7.07. Sorry about that, but that's where we get that. Just because the square root of 50, why is that? What is 50 factor? 50 factors to 2 and 25, and so that's 2, 5, and 5. So I would have 5 square root 2. So hell yeah. So I would have that, and then this would be 4. This would be 1.4, and so it would be the equivalent of 14, but divided by 2. So that's 7 point. Yeah. So I get it. All right. Hell yeah, and that's the best I could do. You know what I mean? So it's an actual mathematical, proof of like, and because these are negatives, when I increase the velocity, this becomes a more negative value. And no, that's not what I would want. No. When I increase this velocity, this becomes bigger, and then therefore this becomes a. Let's forget about the negatives. Mess me up. But when this velocity gets bigger, what's that going to happen? This number is going to get smaller. Is that what we want? So let's say this number was like -5, and this number was -5, and we're equal. And then we're going to increase this. That means that, and then forget about the negative for a second. Yeah, this is the mental trip. If this increases, this goes down to, let's say, 4, because it's got to be smaller. And then I have -4. So now I'm comparing -5 and -4, and -5 is smaller, and that's what we want. We want the circle to always be a smaller number, and then this to always be bigger. So there you go. As we increase v, yes, so there you go. So I think this is the actual answer that you would have in a textbook. I'm just fascinated. I don't know if there's any mathematical proof of like, hey, I have two equations, like, are they going to touch when I can adjust one of the other variables? So that's it. That's what I did. So, hell yeah. I don't know, that's interesting. Alright, so thanks for joining me on this one, and that's a video.